Philip, can you start us off with walking through how one sends a text file or some kind of data payload on the modern web? And then after you've done that and told us about how it's wrong and bad, I can go through my ideas for how we should be doing it instead, and you could tell me why those are also wrong, and then maybe we'll get somewhere productive. All right?
Right. Yeah, we can talk about a text file, because if we tried to talk about how to send like a document, especially even a static document, let alone a dynamic document, then we'd just be here all day. So for a text file, you know the way you feel like you do it when you just go to a text file is that, like, you open your computer, you go to Chrome, you go to Google, you find some text file, you click on the link, and then it shows you the text. Like Chrome shows you the text, and this takes like depending on your connection, it takes you like a second to load, depending on how big the text file is, and depending on like how you got there. The second is like a high thing, but it's actually not that high if you have like a edge connection or something. Like, I've been on a lot of trains, and you don't have that good Wi-Fi. But the like end-to-end cycle is that first you have to figure out what even file, like what texts are you trying to access, like what's the resource, and that's from like the URL. And the key part of that URL is the domain name, which is like, you have some URL, it's like example.com /thing/more-thing.txt.
Feels like you need a thinner brush.
Yeah, but also I'm too lazy to.
But let's to be fair with my example later, let's assume that the person already has an IP address that they're connected to. So we've already resolved the domain. We can talk about the replacement for DNS later, but let's just do the connection first.
Okay. So you've determined your IP from this, which we can hand wave how we got that. Now we have the IP address. All we know is the IP address. And now, first thing we want to do is, we want to establish a connection with this, with the server at that IP address, which means we also need to know the port. So we're given some IP address and a port, right? And it's in like we know this, and first thing we do is we start a TCP connection on a web server. It's usually port 80 or 8080 or 443. 80 is usually for like HTTP, and 8080 is and 443 are like HTTPS, I think. Don't quote me on that.
Isn't 443 also IMAP, I think?
Potentially, yeah.
I think so. But the port isn't that important, or isn't as important as people may think, right? Because this could just be like
you can host the server on any
everything.
Yeah, of course, there's going to be an IPv4 address that's going to be converted 3 times when you translate it across the different networks to like 7 different ports, and then there might be firewalls in the way and stuff, but that's fine. God forbid you actually establish the connection easily over the internet. First thing you do is you're probably going to send a TCP packet, and it's going to be the TCP SYN to say, like, synchronize with me. I want to start a connection with you.
Does it really stand for that? Is it synchronize?
Yeah.
Wow. I
And
didn't
then
know
there's
that.
to end a connection, it's fin, which is like finalize.
Right.
And then there's the sin ack, I acknowledge, and the fin ack, I acknowledge the end. So you're going to send a sin to the server. I guess we can draw the diagram for that. You do a sin. And this is just to establish the connection. There's no payload to this data, I'm pretty sure. There might be a... No, I don't think there's any payload. So there's a TCP SYN.
Right. So you're forbidden from adding any data to this.
Yes. Don't quote me on that. It might be possible to put it in the IP packet, but like it wouldn't.
Right. You can always put stuff in delivery. The IP packet, I think.
Yeah. And then if the server is up and running, the TCP, it'll send a TCP ACK, SYN ACK, pretty sure. So it's like, hey, yeah, I want to synchronize too, and I'm acknowledging that you want to synchronize. This isn't special, I'm pretty sure. I'm pretty sure it's just you have this. You also send the SYN flag. The SYN bit is set, and then also the ACK bit is set. And ACK bit is like used in it's used for all acknowledgements.
Mm-hmm.
So you send that back, and then the TCP on your end sends an ACK. And of course, you can't do this. As Google Chrome, the user mode application can't like construct a TCP packet and like send it. Maybe Google Chrome can because they do some horrendous insanity in their 30 million lines, but like a regular like Berkeley sockets user.
Yeah, I actually researched this a little bit because you can imagine if you want to send ICMP packets, how do you do that?
Yeah.
And actually on Linux, if you are root, you can send and receive just IP raw without any middleman.
Yeah, on Windows you need administrator privileges to send ICP. Like trace route or trace RT requires a administrator. Right. I'm pretty sure. So like God forbid that you have the ability to just send an IP packet or even worse an ICMP packet. That would be like the user using their computer for their own purposes is verboten, right? So. This is like I'm in my C code. I'm calling like what is it? Oh, now I'm on the spot. I think it's like first you have to bind the socket. It's like all the socket API stuff, which I'm not a big fan of. I don't do streams that often. Like most of my work has been on UDP.
Yeah. Okay.
There's bind. There's accept. There's all the Berkeley socket stuff, and then there's listen. The server's gonna listen, right?
Right.
All that stuff, all of it's going through like these OS APIs that prevent you from like they construct this automatically, and like if you accept a connection or whatever, that's gonna secretly behind the scenes turn into like, oh, I'm setting this one bit on my packet that says I'm gonna hack it. And I'm going to send.
Is the idea here that when we do a SYN-ACK, it's because we now get a new TCP port? Like on the way back, we say, hey, I see that you connected to me. I want to, I guess, synchronize with you as well. And then it gives a different port number to send future packets through to.
No, I don't think it's allowed.
Are you sure?
The identity of a TCP connection is the source IP end port and the destination IP end port. From the perspective of each end.
Right. But from the perspective of the user program, you get a different thing back. You get a different handle.
Right. Yeah. Because you're going to be like, once you make the connection, the API is going to give you a handle. Yeah. For that specific connection. But don't quote me on that. Berkeley sockets is like, I'm not a super big fan.
Yeah, but okay. So this layer has provided us with connection differentiation. So we could tell.
Yeah, the key here, the value here in the SYN and the ACK from a networking perspective is that both sides now know that it's possible to deliver packets to each other. because from the client's perspective, they've sent and they've received in response to their sending, and from the server's perspective,
Right.
they've received and then they can send, and then they can also receive again in response to their sending because the client sends an ACK after that. That's why it's a three-way handshake.
Okay.
Because it's like both sides know there's three packets involved, and both sides, if both sides receive, then they both know that they are connected.
Okay. And we've lost, say, for our example connection. Well, you've been testing this recently. What should we assume as our example ping time?
I mean, okay, sure. If you're touching a server that on like a sort of normie household connection, if you're touching a server that's like within the same country as you, I mean, countries are big, but like if you're in the United States and the server's in the United States, it's going to be like low end is going to be like 30, 40 ping. If it's the same city, you might get like 20 ping.
Interesting. And I guess this is better with fiber. I know from like when playing Apex Legends in Stockholm, you can get, on the server in Frankfurt, you have like 2 milliseconds, which 70. Is really, 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 really good.
Ooh.
But that's because it's fiber optic the entire way.
Yeah, you have a straight line. Yeah. No, like broadband or not broadband, like cable. I know I'm in Poland right now, and the connection I get to the Netherlands is like 60, 70, 80 ping.
Right.
Other people in the US, depending on where you are, you can get.
So should we say 70 ping then as a sort of typical?
70 ping is totally like expected. That's the kind of thing you have to handle and like be aware of. And I've been because I've been doing some netcode testing. I used a VPN for Pakistan, and I connected to a US server, and my ping was about 300.
Right.
And that's sort of like a higher case, but like there are people in Pakistan who want to connect to servers in the United States. Like that's not that surprising of a thing. Yeah. And that's not like an edge case really, unless you like don't care about like the world connecting, which is sort of what the internet was made for.
It should also be said that if you are Google or like a big sizable web company with customers everywhere, you play the game of CDNing very hard, where you've like
you like host servers everywhere, and then you have the distributed data problem of like, oh, now I have to install a database on every server so that the latency is low, but then I have this like replication problem where I have to design databases that are like distributed services that all touch each other and can like eventually agree on some consistency, which is like sort of the mind killer when it comes to like software complexity and robustness.
Right.
Because the moment you have distributed microservices or even just macro services, it becomes like harder to debug, even more than it already was, because there's over a network and it's a parallel programming problem, which we can't understand right now as a society. And it's also just there are like on Linux boxes that you have to SSH into and run GDB. So like the debugging experience, even when you can debug, is like not ideal.
I was just going to say, like, if we imagine sort of a small web experience of I'm connecting to some guy's server and he has one server and it's on another continent, we I guess can assume more like 150, 200 as typical.
Yeah,
or even maybe 400.
The ping time on a good connection from Buenos Aires, Argentina to Shanghai, China, is about 300 milliseconds. That's like a good connection. Those are antipodes. Like, so they're on the opposite. They're literally on the opposite sides of the world. Like if you dig a shovel down into the earth from Buenos Aires, Argentina, you would literally end up in China, because they're like that's what an antipode is. It's like the opposite side of the Earth. It's one of the few places on land on Earth where they're opposite. But it's basically the same thing as just like compute the speed of light on a circumference around the Earth, right? Or divide that up by 2.
Right, but it's worse
like,
because you have processing
maximum
time at all these nodes. I'm pretty sure that SpaceX, if you both are on Starlink, it's actually way better because they just do like lasers between all the satellites.
Yeah. So your speed of light figure is be like, I didn't do the math. I think it's less than 100 milliseconds actually for halfway, like to go around the Earth, halfway around the Earth. But it's the practical like ping times that have been measured empirically right now. There's online data for this. He's like 300.
Okay.
But that's a good case. Like I said, the Pakistan to US was on a standard VPN from Poland to Pakistan to the US, based on the VPN, was like 300. So that's including like a realistic like processing times and your application processing time plus your operating system processing time plus every middle box's processing time plus the server's processing time plus the server OS's processing time. All of that multiplied by 2 because you do one way and then back, and that's the ping. Right. It's a round trip.
Okay, so let's say 160. Is that reasonable?
Yeah. Well, maybe for the math, maybe like 150.
Yeah, okay, sure. So we've lost 150 milliseconds by this one round trip.
Oh yeah, the first round trip is 150, and then remember it's a 3-way handshake where we have to deliver the ACK as well.
Yeah, but we don't have to wait. But do we? For that?
Yeah, we can start sending other TCP packets with real data in there. They'll just come after.
Okay, let's continue then. What happens after this initial handshake?
Well, this is on the web, right? So this is a text file on the web, and it's hosted on some web server. And the way like Google Chrome is going to connect to it is like, first you establish an HTTP connection, and then inside the HTTP connection, you basically say, I want to upgrade from HTTP to HTTPS. Now, there's a lot of different versions of HTTP and some different versions of HTTPS. So this isn't always true. This isn't like guaranteed to be true. In fact, like, if you're Google Chrome and you're connecting to a Google server, then you're usually gonna get like the hottest, freshest, newest thing that Google has designed for you to make sure that Chromium can be the only viable web browser. But there's gonna be some cases where this is gonna be what happens. And don't quote me on the details, but basically there is like a HTTP header. What are they called? Yeah, headers. Called like upgrade connection or something, and of course there's an uppercase U and like a dash and like connection, because of course this is all text based, which we'll talk about.
Oh, really? We go straight from we have a stream to now we're doing text.
Yes. So basically, the moment we have a TCP connection, of course, the way HTTP works, because it was designed in like the 1989, where this might have made more sense, and doesn't anymore. Once you have a TCP connection, this guy just starts sending letters, like the letter H and the letter T and the letter T and the letter T.
And do you think, is this like an ARPANET inheritance that people thought it was smart to do things this way?
I think so. I mean, I know we talked about how email was like entirely Yeah.
Yeah, well,
The email protocol is
yeah,
just
email is still like you connect, and even if it's a secure connection, it's encrypted, but you send the email over as text, and all the file attachments have to be converted into a text form that doesn't violate. Like if you send, they have like an 80 line character limit. So if you send more than 80 bytes, or you can only send like 80 bytes of valid ASCII, I think, or something, or maybe UTF-8 is now okay. You can only send 80 characters, and then there has to be a new line, because I think this has something to do with when they detect the email is over. So like the email is over based on like there were 2 returns in a row or something.
Yeah, we'll get to that. Yeah, this is, you'll see all the same stories here with HTTP. So the way HTTP works is, I was saying we were sending individual bytes, but of course we're good engineers. We understand that sometimes it's important to be efficient. So when they did like netcat or whatever, or when you're a guy on a terminal typing in letters, and you're trying to type in the HTTP header manually, because like that's probably something Tim Berners-Lee did at one point. We designed like Nagel's algorithm. I think Nagel's algorithm.
Yeah, it's Nagel's is.
Nagel's algorithm might be a little bit different.
Oh, yeah. Nagel's is on send. So you wait a little bit before sending data in case there's more data you could have put in the packet.
Exactly. So this is similar to that. I think there's a name for this one specifically, but it's pretty basic. It's just once you hit a new line, because of course this is text, so we have text like ASCII text. Once you hit, not /n, /r/n, because this is like Windows compatible, or like
Well, this would have been on a teletype, probably.
On a teletype, yeah. So you do a carriage return and a new line. Once you get a carriage return new line, then you can deliver this as a packet, because this is more efficient than sending individual like one packet and one byte. There's way huge overhead on that. So what you do is, the way the HTTP protocol is specified is that the I'm trying to remember. I think it starts with my fingers are crossed that it starts with the letters HTTP, because otherwise that would be terrible. It might not. I think it's like HTTP 1.1 or 1.0. And then you type get, because of course you're doing a get request to like get the text file.
Right.
Give me the text file.
Yeah.
And then you type in, I don't have enough space here. Let me do that again. So you have HTTP 1.0 get. And then you have the URL, but without the domain name, because the domain name came from a different way,
right?
Or it came through the domain name system. So we have like my file.txt. Now there's something a little bit suspicious here, in that I'm pretty sure actually the way it works is that you type get first.
We've already leaked the file we're accessing, right? Because we're not encrypted yet.
Yeah, so this is what would happen in HTTP 1.0.
Okay.
I'm going a little bit historically first. So I just wanted to get the whole line in, so as an example for how this algorithm works. You have all this gets put in a packet, because if you were typing this out in a terminal, which you can do, and I've done before, you don't send any packet requests until you don't send any packets until the line is finished. Like in your SSH or whatever, you can actually notice this, I think, usually in SSH. Typing in the terminal is not that bad until you press enter, and then it takes longer. But don't quote me on that either, because these systems are really complicated, and so God knows what is actually going on. I just wanted to get that principle out there that like you can buffer up data until there's a clear point at which you can separate out the data, which of course we do on lines here because lines. Who would ever want to buffer data more than a line?
Right, and this is because we had the concept of packets that we were sending, which we then erased by putting the stream abstraction on top, and then we need to have an algorithm that's like automatically packetizing that stream.
Yeah.
Because otherwise it would be inefficient.
Yeah, because what's really happening behind the scenes is that like if this is a really long line, you can't fit all that in one like packet. You actually don't know how big the maximum packet that can be delivered is for any particular connection across the world, because it depends on like all the hops.
Well, there is a minimum.
There's like a specified minimum which you're required to handle, but it's very likely that the minimum unit in between all your entire path is like bigger than that, and you just don't know.
Yeah, you need to
like
test.
For example, the IP specifies like 576 or something as the minimum bytes. But like the average Ethernet frame, or like the Ethernet frame specification is like 1400 or something bytes. And if you like subtract the IP header and the TCP header, that's like 1392 or something that you can use, I think. So it's like you very likely can use an Ethernet frame, or like very, very, very likely can use Ethernet frame as your MTU, but you can't guarantee that. And so like you have to empirically like send a big packet and then shrink it down until one of them gets ACKed, and then you choose that one. And that's actually dynamic because of course the route that you have from your client to the server can dynamically change, like from here to here to here down to like some other thing that has a different MTU and is like more efficient or less efficient, just because the internet decided to route you differently because like a middle box went down or something. Or like a nuclear bomb went off in this region of the world, which is the reason that ARPANET was invented. So you need to dynamically like adjust your MTU and adjust to your ping times as well. But yeah, so the bottom line is that you're going to be chopping up big packets into little fragments and sending them individually. Now, I think my understanding is that IP has fragmenting in it, but also TCP decides that like we're not going to do IP fragmenting or something, and we're going to determine the MSS, minimum segment size, because of course these packets are not called packets; they're called like segments.
Yeah, that's actually very reasonable, because I think what people discovered is that actually fragmenting was like a bad idea to have that on IP. So
yeah,
IPv6
you want to
does
put it
away
in the
with fragmenting, layer. Except you can add it back in by extensions, but I don't know that anybody does that.
I mean, I'd hope not, but you have to support it because it's in an extension.
Well, no, but that would be like, oh, if all the guys on your route support fragmentation, then you can add fragmentation for the guys with the niche use case on their internal network who want fragmentation. It's the same thing with jumbo packets.
Exactly.
Like you can query and see all the hops from me to my destination support jumbo packets, the jumbo packets extension. So I can now start sending 2 gigabyte packets between all these hops.
Yeah, which is kind of based.
Yeah.
It's the marvels of like modern internet, where like many of these data limits are completely irrelevant, but we still.
I think the reason for the extension is that it's really for like, oh, the network might support sending more than 56K packet size because the size field is 16 bits, and so for
65K.
the jumbo
Right,
packet
65536.
extension, the jumbo packet extension just makes it a 32-bit number.
4-byte header.
So you get up to 4 gigabytes max packet size. Although I doubt any packets are actually that big currently.
Right, that's pretty good. Yeah, I'm all for that.
Okay,
You
so
know, it'd be reasonable to send more than 64K in one packet.
yeah. So
yeah,
where are we?
but
We're sending this text in the HTTP request.
Yeah, and I'm sort of going back and explaining that these, like this stream, this so-called stream, is not really it's not sent over the internet as, you know, byte by byte by byte. It's not even sent by like packet by packet by packet, because of course some of these packets are actually not going to come through the first time. So like I'll send you the start of this, like the H and the T and the T. Obviously the data is much bigger than just 3 bytes, but I'm just going to put it as an example. Well, there's also a space character encoded here. So you can see I'm trying to send these packets that's like HTT P space 1 dot O space GET, but of course this middle one fails to be delivered. Now that's either because one of the hops has like a buffer and the buffer got filled up and is like, all right, well, I throw my hands up. I can't do anything with any. I have too many guys are trying to touch me right now, so I'm going to just drop some of the data, and you know, it's your job to send it again.
Yeah, that might be interesting, just to cover. Well, at least I find this interesting that on the actual infrastructure delivering all the packets, like they don't have spare space over. Packet drops happen because the memory on the router gets filled up. So, or the buffers or whatever that it's using. So it receives a packet, but does not have space to put that data anywhere. And so there is no other option than to just throw that data away. Or like it in a sense fails to receive it because there's nowhere to receive into.
Right, yeah. Yeah, I assume the data comes in on the network, on a chip on the net. Like it gets into a buffer, and then it has to just discard. It can't copy that buffer out into main memory anywhere.
Yeah,
and it has to just discard it.
Yeah.
Although I'm probably giving middle boxes much less credit than they deserve, in that there's probably some wacky hardware, like crazy hardware going on, where like there is no interface card. It's just the card is just directly writing to memory.
Yeah. All the backbone stuff is definitely that kind of super advanced, high speed stuff. And well, the interesting thing as well to imagine is that the only reason the internet works is because everybody is collaborating, and there are kind of like loose incentives that govern this. So basically, as packets start, some boxes overloaded, packets will start getting dropped at random. Because it's, by chance who didn't fit, right? And then basically, it's the folks on both ends of the connection who notice that packets aren't making their way through, and then they lower the amount they're sending. They basically send slower. And so, this system only works because we drop packets. And then, all the endpoints are sort of incentivized. They want actually their packets to get through, and the most packets get through on the network if people send as much as possible without overloading any individual box. So everybody is sort of incentivized to be sending as much as possible, but not too much, so drops happen. And so there's an algorithm on both sides that's trying to figure this out, is like sending faster and faster and faster and faster. Ooh, some of my packets got dropped. Let me rapidly back off, and then slowly increase again.
Yeah, and I'm pretty sure it's actually relevant that the packets are dropped at random, because I think there's some math theory that says that just doing it randomly is actually like a way to keep the system more robust. This might not be mathematical, it might be empirical, but like that you're doing it randomly makes the system more robust than if you were to do it like preferentially.
Well,
And this
yeah.
allows
As
this also
Mr.
allows you to choose different hops.
Yeah, as Mr. Fielder can tell you from Gaffer on Games, that it's actually a big problem when routers in the middle, they actually, I don't know about all of them, but definitely some of them have a preference for dropping UDP packets, because they can tell the difference between TCP packets and UDP packets. And TCP packets
Yes.
UDP packets may be retransmitted if they're dropped. TCP packets will definitely get retransmitted. And so whatever engineers decided to make the decision that if the buffers are full, they drop the UDP packets first. Now this means that like on a home network, you can easily end up in a situation where you're playing a video game and everything's fine, and then somebody starts not streaming Netflix, but somebody starts downloading a file, and your game is just hosed because the download the program doing the download over in the web browser or something fails to share the connection with the video game because the video game is basically deprioritized over. So in a way, you could think that the internet download doesn't notice that this video game traffic is there because the video game traffic gets squeezed out first.
Yeah, exactly. And you said the important thing where UDP packets may be retransmitted, but TCP packets will be retransmitted. Similarly, UDP packets may be a guy watching Netflix through some like UDP connection, but TCP packets are much more likely to be a guy watching Netflix over the web, and so the internet service provider needs to make sure that Netflix.com is getting their packets through, and the lowly video game guy like isn't just that important to their services.
Well, this is without net neutrality, right? As opposed to
yeah.
I think in Europe they're not allowed to do preference based on who's sending the packets, which
right.
Like honestly, it doesn't matter that much. Clearly, the internet works with and without these rules.
Well, yeah, and firewalls are kind of allowed to do port-based discrimination, kind of regardless. Like nobody enforces port neutrality. So
right, and there's email
if you send
stuff
a packet
as well.
on TCP port 80, no one's gonna like reject or like firewall a TCP packet on port 80.
Right. Yeah.
Unless they sniff it, which you can do because what we've talked about so far has been unencrypted.
Yeah. And the argument as well for actually against net neutrality is if the ISPs look at their network and say, hey, here are some people, some people we have a lot of people trying to use our network, and then we have Netflix, and Netflix is Netflix for free, for no cost, gets to just hose our network with packets and ruin everybody else's day by using all this traffic. And by letting the ISP go to Netflix and say, hey, Netflix, we want you to pay us money for all this traffic you're using, actually gives a financial incentive for Netflix to do a better job compressing their video streams, moving the streaming servers closer to where the content is actually going, etc., etc.
Right. Yeah. Yeah, I can buy that. I used to be a super like anti net neutrality like Redditor, like because I was on Reddit and I was like, wow, net neutrality is like actually evil and gonna destroy the internet. And then I think I like dropped off and didn't pay attention, and I think they got rid of it in the United States.
Well, wait, it happened under Obama, and then it got removed under Trump, and I'm not sure anybody noticed the difference.
Yeah. I'm pretty sure that's something like what happened. But now I've just been so like out of the loop and not using Reddit that I'm like, oh, it's actually, I have no opinion anymore about net neutrality. I want to do more research on it.
Right. Yeah.
But yeah, what you said is like a totally viable story that I could buy.
Yeah. As always, there are pros and cons
Uh,
on both sides. The argument for net neutrality is obviously, it's kind of extortion from the company. So you're
right.
relying on them not being asses.
Yeah. I think there was also I assume the reason that like the people were so outraged about it was just that they were like the consumer advocates who like felt like they would have been best served by all their connections being neutral. Although
I think the real reason
that might even be
actually is
arguable
that
in itself.
YouTube doesn't want net neutrality because it's obviously not an ISP, but is a massive consumer of internet traffic, and so YouTube were against it, and so they like deployed their memetic power to make sure everybody was.
Yeah, that's entirely possible. I'm going to move this graph up so we can have more space.
Okay, where were we? Popping the stack, as we say.
Yeah. Yeah, so we're sending a bunch of packets. So we're sending like a data packet. Now we've established the connection, and what's likely going to be in this initial stream is an HTTP. Like I don't know exactly how this one's formatted, but it's like it might just be a get on the empty, a get on the home page, and then it says like upgrade connection. I don't know if there's a special request type.
It doesn't really matter for this discussion, maybe.
Yeah, exactly. So this is like semantically, this is the stream of data that we want to deliver, and it's got some. Of course, it has like encryption method, right? Something like, oh, here's how I'm going to encrypt the data, or here's how we would like to start, or here's what version of like the TLS we're going to use.
Isn't that in the HTTPS header though? Because you can initiate an HTTPS connection directly, depending on the link, right? So if you have an HTTP : / whatever, and if you versus an HTTPS : / those will take different connection times because one of them will go directly to HTTPS, the other will first do this HTTP upgrade query.
Yeah, and of course it has to ask. I'm glad you pointed out that it's a query because the client has to ask, "May I please upgrade the connection?" And the server might say, "No, you're not allowed to do. I can't do that for you. Sorry, we have to live in HTTP land." And maybe the client will just like reject the connection, or do like the annoying pop-up that I always see on Chrome and Firefox, where it's like, "This connection is not secure. You need to like, you're not allowed to do this," or like,
it's like the normie protection because it's like for a technical person who wanted to read the old blog, they know that they click advanced and then continue, but for like the pensioner, it's like, oh, something's happening. I could have my credit card details stolen.
Yeah, exactly. The irony is that that's designed for like, oh, there's a guy like sniffing your connection, middlemaning your connection between the server and like trying to like inject his own web page, which is a threat. But the practical case where the middleman is sniffing your connection is the Starbucks Wi-Fi that wants to prompt you to connect to their Wi-Fi first and sign in, or like accept their terms and services.
I actually want, because that's just I think that's so weird. Because for Serenum, we'll get to this. Basically, that's gonna prevent me from using Serenum in a in a Starbucks, but it's only legal, right? That one is like, because there's no because connecting to an open Wi-Fi network doesn't constitute having agreed to the terms and conditions, because there's no way to find out the terms and conditions via the Wi-Fi protocol, right? Can you imagine that? Like, if you could do like press the 3 dots on any Wi-Fi network and it like showed you the terms and conditions before
Shows
connecting.
you the terms and conditions.
No, we don't have that. Instead, it's like
That'd be amazing.
I connect, but now if I do something crazy illegal, I think Starbucks is liable. So they have to add the HTTP thing to put in their own web page so that you can press a button. So you cannot read the terms and conditions, but press the button that says, yes, I did read the terms and conditions. So that now when you do the mega illegal thing, Starbucks is not liable.
Their fault.
You agreed. You're actually in violation of contract because it said in the terms and conditions, don't do mega illegal things on our network.
Don't
don't torrent
a dark
on
web
network.
drug service from the public library.
Yeah.
Or the FBI will find you. Just close your laptop fast enough, guys. Anyway. So that is what middlemaning practically ends up being like for me when I go traveling. It's not like there's a threat. There's like a Mr. Robot dude trying to intercept my Happen Lance development streams. So, which by the way, most of our internet activity is like on public social media anyway for like a majority of the users. So the idea that you need to like watch that connection is like kind of
no, it's to stop him from like inserting things into the video stream.
Yeah, dude, I didn't say that word, guys. It was a middleman. I was running on HTTP, guys. The middleman inserted into the video stream.
I didn't
a
tweet
deepfake
that.
of my mouth and voice.
I get to keep my job. I didn't tweet that.
Yeah, I got hacked.
Yeah.
Someone registered a domain name at the domain that I accidentally created when I did g-20.in. on Twitter, and the link auto resolved. Anyway, so there is going to be this scenario where you want to upgrade a connection, and we're going to just assume that it succeeds. It's very likely to succeed, or unless it's a strange connection. Again, it's actually not likely that you'll have to upgrade the connection because you're going to be on HTTPS in the first place. But of course, this is a thing that exists as a historical artifact, or existed at some point, and like sort of has to be supported kind of, for the like principles of the web, which is that you never like break backwards compatibility and everything has to be internally compatible, which of course somehow is a principle that we have despite the like relentless link rot that happens throughout the entire web and like eats away at like our web, and makes it even more unavailable than the like GPT slop that's pervading Google already is. But that's another discussion. So this stream, like I said, it's going to get chopped up into into segments, and these segments are going to be put into packets. The difference between a segment and a packet is just like the TCP header, I guess, basically. And the TCP header has some stuff like it's got like the port, source port, destination port. I think it's got a checksum, which, by the way, is not that useful when you like have to do a manual checksum in like all of your applications anyway for different reasons, like an HMAC or something. And then it's got like the length, stuff like that. And then it's got the actual data payload. So these packets are going through, and of course, in the example I gave, there was like these 4 packets, and the third one didn't go through. So the way that would work is that we send our first packet, we send our second packet, There's some. I'm simplifying because there's actually details here where like you can send a bunch of packets without getting an ACK first. But let's ignore that. Can you still hear me, by the way?
I can.
Okay. It'll be very ironic if my Wi-Fi goes out in the middle of this conversation. So the client doesn't wait for. He'll say like, here's packet 1, here's packet 2, here's packet 3. I did this diagram wrong. Wow, that's wonderful. This one failed. Yeah. And this one didn't go through. So like there's a failure here somewhere trying to establish this this connection, or trying to deliver this packet. Again, like I said, one of the hops could have buffer overflowed or something, and there's just no room to put the packet. So here's packet 1, packet 2, packet 3, packet 4. Somewhere along the line here, the server will say like, okay, hey, the last, packet that I received is packet 1. I've received packet 1. Thank you. I will put that in my application buffer to be received later by the server, to be processed by the server. Or, he might wait a little while. He might wait until he has data to send of his own. Although usually, he needs to wait until that can happen. But he might be like, this 4th packet might arrive successfully, but the server will say something like, okay, well, I missed number 3. I didn't get that. I got number 1 and number 2. I didn't get number 3. So the most recent packet I've received is number 2. Okay. So the 4th packet has actually come through, and in the buffer, I'm pretty sure this is how it works on the OS side. We don't have visibility into this because how dare we have visibility into how the stream protocol works. There's a buffer that says like, oh yeah, I've received packet 1, it's over here. I received packet 2, it's over here. And I've received packet 4. I'm waiting for more data. So like this is the free space or whatever. Something like this.
Maybe in TCP they do the cool ring buffer.
Potentially,
with holes, yeah.
Yeah.
Although they're variable size,
yeah.
so I don't know if that would be smart actually.
Yeah, you can still do the ring buffer with holes, but you just have it be a pointer to malloc to memory.
Makes sense.
And you still get the semantics nicely.
Hold on. Continue this explanation. I need to feed this cat. Hold on.
Okay. I'm gonna be commandeering.
Well, yeah. Don't hold on. Keep going without me.
Yeah.
Just for a moment.
So there's this gap here because, of course, this server has not received this this 3rd packet. And now, what you might think to do is like, if you're like trying to design a protocol, is say like, oh, why don't I just send a packet that says like, I've received packet 1, I've received packet 2, I've received packet 4, but I haven't received packet 3. Can you send me packet 3 or something? But that's a little bit complicated, and it was like the 1970s, 1980s, I think 1970s. So they were just like, okay, we can't really afford to do that right now. We're just gonna do a thing where we just say, we'll send the most recent packet for which all previous packets have been received. I've received everything up until 2, and not everything afterwards. So I didn't receive packet 3. And so now the client eventually receives an ACK. Now the ACK bit will be set on this packet because we're acknowledging some stuff. I don't remember if ACKs are sent as separate packets. I think they can, but that would be kind of wasteful. So I don't expect that to be done in modern times. I would hope not. So usually we just like bundle it in with other data payloads, right? In this particular case, because it's early on in the connection, you can't really acknowledge, or you can't really send data along with the acknowledgement. all you can do is acknowledge because you haven't processed anything yet. But it's also good for like pinging. If you just want to like keep the connection alive, you can just send a packet or an ACK or something, and then both sides can know that each other ACKed each other recently.
I acknowledge.
And so, yeah, acknowledge. Thank you for acknowledging. It's by this time, there's a bit of a delay here, you'll notice. It's by now that the client understands, oh, I sent packet 3, but I've only received an acknowledgement for packet 2. The server may have sent an ACK for 2 here. But by the time it lands here, the client doesn't know, even let's say it arrived before we sent 3, potentially. It's unlikely, but let's say. The client will know okay, well, everything's up to date. I've sent packet 2 and received an ACK for packet 2. And even after packet 3, if we receive an ACK for packet 2, we have to be okay, well, I received an ACK for packet 2 and I haven't received an ACK for packet 3, but I just sent it, so I can't expect it to have arrived, right? I kind of don't know when really to decide hey, it's been too long. Not inherently, right? Because it's just a connection, and the time that it takes for a packet to arrive is variable. Sometimes they take longer, sometimes they take shorter, sometimes they don't happen at all. And actually, you can actually have congestion where the packets take really long, but how long is too long, right? So that's sort of fuzzy. So you could even receive an ACK for 2 over here, which is kind of recent. And you can still just be well, okay, 3, I didn't receive an ACK for 3 yet, but it's not a big deal because, I expect to receive an ACK for 3 a little bit later. But then there eventually comes a time where it's okay, it's been long enough since 3 that the fact the server has only acknowledged 2 is kind of signaling to me that 3 hasn't arrived. So what I'm going to do is I'm just going to resend 3 and I'm going to resend 4 because all I know is that only 2 has been ACKed. So the thing that I know is that everything after 2 is incomplete because
it sends 4 again as well. So it says 3 and 4.
Well, you only know you have to send 3 again and you have to send 4 again because you only receive the acknowledgement. The acknowledgement is a number.
That's an optimization, right? Because it's basically saying if we dropped 1, we probably dropped more.
No, the TCP. I mean, we can pull up the TCP header. The acknowledgement only tells you one number. It tells you the sequence number. By the way, these are called sequence numbers. It tells you the sequence number of the most recent packet for which everything before it has been received. Acknowledgement number if ACK set. The acknowledgement number just tells you this acknowledges receipt of all prior bytes, if any. It doesn't tell you what got acknowledged afterwards.
Right. But what I mean
so there's no way for the client to know.
You could imagine a scenario where 2 times out, we resend 2. Oh, sorry, 3 times out, we resend 3. Then 4 times out, we resend 4.
Yes, but you won't. Yeah. I see what you're saying, but
that would add latency because we're waiting for each timeout to expire.
Yeah. That would add even more latency to this. But the ACK just could have given you more information about what was actually received and what wasn't. But because it's an 32-bit number, it's one single 32-bit number, we just don't have that information. Like you're saying, we could have just resent 3, under the with the knowledge that 3 is definitely did not arrive because 2 was the number that we got, and then waited for the server to ACK 4 because it's received 3 and 4.
Oh,
and then
wait.
Okay.
Okay. Now I understand. Wait, so you're saying the ACK for 4 is not sent yet?
Yes, that's correct. The server does not send acknowledgements
on a per
for
packet basis.
Individual packets. It sends, here's the number that I got everything before that. Yeah.
Okay.
It's in the Wikipedia. In the wording, it says, the value of this field is the next sequence number that the sender of the ACK is expecting. Okay, I guess I have it off by 1 in this diagram, but it's kind of irrelevant. Technically, it'll say like 3 here because it'll say like, give me 3. Because I have everything before 3, but
that's like,
and then it says,
bad.
This acknowledges receipt of all prior bytes.
Right.
The first
so we couldn't send an ACK for only 4 because.
Yeah.
Right.
You can't send an ACK for individual numbers because then the client is like, oh, well, you got everything before that too.
Right.
But 4 might have been 3 might have been missed in this case.
And presumably they made this decision a long time ago, assuming maybe it was even the right decision for the networks they had then. But clearly it's not good now for the thing we said about random packet drops. Because packets are dropped because of congestion. Yeah, and they're dropped randomly. And so probably the next packet might have gone through. So you don't need to resend it.
Yeah, exactly. Yeah, the next packet may have come through. Now, there are many instances where, your Wi-Fi cuts out for a second, and so for a second, all the packets that happen over that second are dropped. But that's not always the nature of reliability of packet delivery. And I've seen before packets be just completely randomly dropped. That's a real thing that happens in practical cases.
Well, yeah. All the flow control is designed around. We will be dropping packets randomly, because we're targeting some rate of packet drop, right? We want to send more and more and more and more.
Yeah.
It's what is it? It's linear growth in, I think this is the algorithm. You grow the speed at which you're sending linearly, and then when a packet is dropped, you divide your send rate in half. So it's like an exponential back off.
Yeah, exactly. And it sort of grows to meet the...
Yeah. So we're going to be dropping packets at random because that's our method of signaling to all the streams what the capacity of the network is. Yeah.
Mm-hmm. There's actually an interesting thing where the TCP spec at some point, I think still does, say that you're allowed to send 10 packets in a burst without any of this congestion flow control. So you can send 10 packets, and we won't run the algorithm on any of that stuff. And so back in the day before HTTPS on the web, it was kind of valued if you could send all your data, your entire web page, in 14 kilobytes, because that's the size of one Ethernet frame multiplied by 10. Approximately. So if you could fit the web page in there, then you could blast all the packets out before any congestion control kicks in, and you could receive the web page just like that if all the packets actually do come through, which can happen on a reasonable connection. But that'll go out the window when we talk about encryption. Because by the way, the other thing is that these get sent in a blast without having to wait a round trip between each thing for like ACKs or anything. You could just get blasted. It's just the single round trip time. So it's a low latency response as well, which is the important thing, or which is one of the important things. So the protocol doesn't tell you specifically which packets got acknowledged and not acknowledged. It just tells you sort of everything before N. And so if you look in this scenario, like we said, or like you said, like we could have this scheme where we acknowledge 2 and then 3 gets sent, and then we acknowledge 4 because 3 got filled in. This means you have a higher latency if 4 didn't get acknowledged. If 4 didn't come through, then we'd have to wait and say like, oh, 3, we're ACKing 3. And now we're like, oh, okay, crap. I now understand. I've come to understand that 4 didn't get through either.
Yeah.
And so
that said,
I'm going to send 4 again. And now the latency on this is
speaking
high.
For this method, if presumably you sent these packets from the client in very rapid succession, and so the timeouts should also be landing in very rapid succession. So I don't know how much it would add in practice. Probably, maybe they made this decision to save on network congestion for the ACKs.
Right. Yeah, that is entirely possible. Yeah, and so I don't know what exactly is common practice as to whether or not you do individual resends or you do burst resends, which is what I'm gonna with the timeout for this. I think it's because we treat each packet as having its own timeout.
Well, you have to burst resend, right?
Yeah. So what would happen is that you don't have to.
Well, yeah. You could
this, but
you could send it.
You could wait for each one.
Yeah, and then presumably the next ACK that comes back will tell you how much of the packets afterwards got through. But
got through, yes, yeah.
You could do that very.
And then you could avoid, in this particular case, you could avoid resending 4. If you got an ACK for 4, because you'd be like, oh hey, I got 4, I don't need to send that. But that's just not efficient for latency. Because again, there's really high latency if it didn't come through. So what we do is we time out 3. We also time out 4 because at the point in time that we time out 4, the most recent thing that we received is an ACK for 2. We send 4 out, and then the server's going to get 4 again if it got it, or for the first time if it didn't. Which it's worth pointing out that a packet can get sent multiple times and be received multiple times. And so when we receive packet 4 again, we just discard it because we already received it. You could do like a check to see if it's the same packet, and then that could be a signal to you that either like something's going wrong. Yeah, but it's just not. It's just
because you already should have put a checksum on your packets to make sure they're not tampered with. Or when we get to encryption, they just will fail to decrypt if they've been tampered with. But that's separate. We'll get there.
Yeah. Well, you could even change. You can change. A middleman could change the checksum anyway.
Yeah. Which.
So it's more like.
I'm making suggestions that assume a datagram model all the way up to application layer, which is what I'm going to be suggesting later, but that's obviously not applicable to this.
Yeah. I want to point out that this buffer that I'm talking about is OS layer and is not exposed. I was going to talk about this. Is not exposed to the application layer, or it's not easily exposed. Like not through like any Berkeley sockets API that I'm aware of.
Yeah.
And
not even in the web browser. Okay. Like Google has not hooked us up with like web TCP. There's web HID, where you can, through a web API, talk to USB devices, but there's not web to web look at the buffer.
Web connections. Yeah,
Web connection. There's not even UDP, but there is USB hid.
Yeah, well,
I'm pretty
to what they did.
I'm pretty sure you could operate a USB in some very funky setup. You could probably construct a situation where you operate a network device over some USB thing manually from a program in the browser over USB hid to get yourself some UDP connections.
Some UDP packets. Yeah. We'll get into UDP. Yeah. So of course this is an OS like TCP internal buffer that is not exposed to the application, not easily. You might need like root or something if you wanted to look at this, or you might even need like a kernel.
No,
network driver.
You just need root. But if you were doing it root, if you have root, you can do it yourself, and therefore be able to look at this buffer.
Right.
But I don't think anybody.
Right. You can do it. Yeah. But I think if you have root, I don't think you can like look at an existing TCP connection or create a TCP connection like through the OS APIs.
You could probably sniff it.
And then
so what you could probably do is you could probably sniff and see what Wireshark see what stuff came through, and then infer what the buffer looks like.
Yeah, that's wonderful. But of course, you still need kernel to actually look at the buffer because it's somewhere in the kernel.
Yeah.
Because we decided that all our network interfacing is gonna go through the operating system, for speed.
Well, isn't it for like API? Like they didn't imagine that.
Yeah.
This is like
it's
Unix days. It's like you can't really. I thought it was for like the like Unix vision of the only APIs I can rely upon are the POSIX provided ones, because otherwise how am I going to make portable software? And so of course, isn't it great if POSIX provides as much useful functionality as possible?
Yeah, exactly.
And I mean, dude, we don't want to put this in glibc. I mean, are you crazy?
Yeah, we don't need more stuff in there. Okay, so this fourth packet is going to arrive, and it's either going to be successfully received or not, or it was received or wasn't received. If this second one drops, well then you just go through the same rigmarole where it's like, I still didn't act 4. I only act 3. Give me 3, please, or give me 4, please, and then it has to do it again, and that happens over and over. And I think there's back off on the resends. So if you resend quickly, and then you resend a little bit slower, and then you resend a little bit slower.
Well, as you're dropping, each time drops are happening, the sending code is like, okay, divide the send speed by 2, divide the send speed by 2, divide the send speed by 2.
Yes, and it's worth noting that again, we're assuming, when the client observes that a packet has been dropped, the client presumes that that's a signal from the route that the data is being sent too fast and therefore needs to be slowed, which is why the rate is decreased on a packet as the resends fail.
Yeah. And they developed these algorithms. Apparently, they developed these algorithms in the 80s because before then they didn't have them. And what you'd get is I think there was some event where like they built all this really, really cool infrastructure, to connect maybe, Europe to the United States. And then and then they have these events where like, the actual data rate on the line fell to like 40 bytes per second across the Atlantic Ocean on the like newfangled crazy hardware. because everybody's resending and
Yeah.
resending and resending, and almost nothing is getting through.
Yes, exactly.
Are you doing the Hawaii example to talk about
I'm doing the
Wi-Fi?
Hawaii, yeah. So, no, actually, I'm just going to talk about resends. So the algorithm for, because I looked this up, one of the original people who looked at exponential backoff is just when you divide by 2 every time, was somebody who's like, what if you had everybody in Hawaii was on like different islands, and they're all touching the same line. And this is in the 1970s.
Before Ethernet?
Well,
isn't
probably.
it like they do this like, what if they're touching the same line? And then they actually, that's what's funny to me is that they developed these ideas for doing wireless communication in Hawaii. I think this got like deployed. Then they repurposed it.
It's probably
for Ethernet, where they said, what if, okay, we'll put one copper cable, like 100-meter cable, snaking through a building, and everybody will have like a device that they like drill into this wire. And now all the computers in the building,
so everyone is literally touching the same line.
Yeah, they're on this same line. How do they communicate on this one line without effectively? And then they got to reuse all these protocols they developed from wireless, all these strategies, including exponential backoff, etc., to communicate on this line effectively. Whereas I guess it's you don't know who's also connected to this line, so there's no like beforehand coordination on who is connected to the line, and people can come and go, etc.
Yeah, because if you're connected to one line and you want to talk, well, you have to talk when nobody else is talking.
Yeah.
Like, give me the stick or whatever. But we don't know who has the stick. So everyone's just sort of talking over each other. It's like a Discord call with more than 10 people. You just need to
perfect.
wait until there's a gap.
Yeah.
But of course, the strategy that is like game theoretically or like chaos theoretically like viable is that like you try to talk and then you might jam, and if you jam, actually you try to talk to someone, and then if you hear back from them, then you're good. If you don't, it might have been because you jammed or because they jammed, but either way you don't know that you got delivered, so you wait, talk again, say the same thing. You can put randomness in it to make it more good, to make it more effective, because you don't want everyone who talked at the same time to exponentially back off and then have their time
right,
and
talk
again at the exact same time.
The randomness is just
the randomness spreads out their
shuffle them, to make sure they find different slots, right?
Yeah. So you talk, you wait, you talk again, you wait, you talk again, you wait, you talk again, and so you just double that. You want to put a limit on that because you don't want to wait too long, because eventually you just decide like, okay, I can't make this connection.
They Mike
Acton from this connection.
Right? They like Mike Acton put a Mike Acton constraint on the total, like, okay, we're never gonna have more than this many people on this line, and so if we're at some point we just decide that the constraints have been broken, or like clearly there's something else going wrong.
Yeah, in the case of TCP, it's like if I resent the packet, or if the time between my first send and like this next time I'm trying to resend the packet is more than, I think it's either 30 seconds or 60 seconds. It's like, okay, well, you haven't acknowledged me for like 60 seconds. I'm going to assume that we are no longer able to talk to each other. Like,
and there's a human element as well.
Is there anything inherent?
You press play on the Netflix stream, and after 15 seconds, you go back and try to play it again because you timed out the video stream.
Yeah, exactly. The thing that's worth noting is that there's nothing inherent to 60 seconds or 30 seconds. There's nothing about the line or the number of people on the line or the topology of the network that has to do with 30 seconds or 60 seconds. That's just a human element. Like, you have to put human constraints on it, because like it would have been hard to figure out what even a good timeout number would have been.
Yeah,
And
especially
it's
since you have
probably
this
dynamic
like
anyway.
yeah, the internet as ever changing, ever uncertain network. It's hard to like make certain calculations about that.
Yeah, exactly. So yeah, this is where we're at. We came up. This is an idea we came up with. It's an idea a very smart mathy guy came up with in the 70s, which got used in a protocol that very smart mathy people made in the 70s. And we use to this day and are using right now in order to communicate over the internet,
Yeah.
in one way or another.
Yeah, the funniest thing to me, oh, maybe we should mention as well that they tried other ideas. So, for example, token ring is never something I have seen or used in my lifetime. But my understanding is token ring was like the competitor system to Ethernet. And the idea was with token ring, you connect all these guys to one line or like one network. And then they can't talk over each other. So they pass a stick around, which is like the token. So there's a ring of like the agreed upon order in which they like pass the token to each other, and they say, okay, I'm done talking. Now you get to talk. And so we like transfer this around. And then you would have the real world thing of like, oh, some device got like unplugged and then plugged back in. So the token got lost. Like the token fell out of the ring. And so all the devices are sitting there waiting for somebody to give them the token.
Yeah. It's funny how in a lot of these, a common pattern in some of these protocols is that like trying to be like robust and rigid doesn't work, and like being sort of random and noisy and chaotic, it ends up working better than being like methodical.
Well, it's almost like there's going to be lots of randomness happening anyway, and so by being intentionally by building algorithms that assume randomness and even introduce randomness, then like any disturbance doesn't shatter the system. It's almost like, you know, if you make a sword or something, or if you forge steel and you make it extremely, extremely hard so it can't bend, then it becomes very brittle and can shatter. And it's actually important for the strength of some steel structures to be forged for elasticity. So they have less total strength, but they actually are able to flex under load and not break.
Yeah, there's that great video. I'm not going to pull it up, of like a Boeing plane that was out of commission, and they decided like, okay, this is going to get destroyed anyway. Let's bend the wings as hard as we can. So they like built this like rig indoors to like grab onto the ends of a Boeing 747 plane wing and just lift it up while like keeping the middle of the plane like secure, and just and it like bends way beyond any plane has ever bent its wings, basically, because the engineering tolerances are so good.
Oh well, yeah, because they were
so
like, this is not allowed to break the wings. They're very important.
Yeah, and so they bend it, and then there's like a moment when it's like a 40. I mean, I don't want to exaggerate, but it's like there's a significant curve, and then it snaps, and it's like a big. It's not an explosion, but it's like a massive snap of the wings, which happens, and it's very spectacular. So I encourage people to look that up.
Yeah, what I find funny about this evolution is that we started out we invented these protocols for wireless with exponential backoff, etc. And then they were temporarily a thing for wired communication with Ethernet. Okay? But then we we basically and it's like a economy thing as well, right? In that this Ethernet line that you'd put in a building, extremely cheap, right? Because it's just a cable.
Copper cable.
And so you get speed gains over wireless because you don't chatter. You don't have as much chatter with everybody else by putting it into wires. Then, for even more speed, we ended up with, actually, we're just going to have point-to-point communication between nodes. And then we're going to have switches so that, computer A can talk to computer B. And computer B can talk to computer C, and that can happen at the same time because they're not on the same cable anymore. But we kept the protocols for some reason. So on a modern TCP link, like a modern TCP connection, I think on like a Cat cable, Cat 5 or Cat 6 cable, it's either 2 or it might be 4 of these twisted wire pairs. And I believe they run separate Ethernet connections. But I'm guessing. But I'm pretty sure they run separate Ethernet. And then the protocol on the wire is this protocol with exponential backoff, assuming there could be many people on the same line, but there totally isn't. There absolutely is nobody else on this line. And in fact, they would probably break for other reasons if you put multiple people on the same line. I'm pretty sure you can't twisted wire pair communicate with multiple people like on the same line. That doesn't work.
Yeah. Well, I don't know what multicast is, but I know that's a thing.
Multicast is on the
networks.
Ethernet. Multicast is your Latin helps you is multi.
Yeah, many throw.
Yeah, but it's also towards, right? So that's why it's uni and multi is because that's like too many people, or one or too many.
Right. It's also worth pointing out real quick that this one line stuff also works not just on Ethernet and not just on Wi-Fi, because, well, I won't get into that, but also works on, like you said, wireless from the before times. And so you can actually set up like a ham radio to just broadcast on like radio waves that the FTC will allow you to broadcast on without like barging down your door or whatever. And well, I think you still need a license either way. That's how amazing radio is. But you can just do packet switching in the same way that like computers do packet switching over cables, just on the radio. And so there's there's a hobbyist collective of like packet radio enjoyers who just like do internet connections over like the radio waves.
Very cool.
Like ham radio, and they're just allowed to do that. Like you need a license, but you can just do it.
Yeah, they have a band reserved to your for hobby ham radio use, isn't there?
Yeah, exactly. So you can just set up your ThinkPad with like connect it to your hobbyist like prosumer like extra cool 80s radio or whatever.
Yeah.
And you can probably do like a telnet or something.
Yeah.
Over that.
And we will be very happy that when the nukes go off, and the backbone is hit, or there's some kind of huge EMP strike, those neckbeards.
Yeah, CrowdStrike gets all the middle boxes.
Yeah. Exactly. The neckbeards will come out of the forest, with their Faraday cage suitcases, pull out their ham radios, and then they'll come out in the hundreds of thousands and reconnect the world via ham radio linked internet that spans the globe.
Well, it's like the ghost soldiers in Return of the King. They just come out of the
Yes,
wall.
exactly. The ghost soldiers in Return of the King. Right, because they're only there for one battle. They're there to set up. They're there to set up communication between Europe and America and China. so that China can start sending boats with IT equipment again, and then they rebuild the network and it's fine. then they retreat back into the forest.
Can be reinstalled. Yeah, exactly.
Or it's like it's only there so that we can get the patched version of the firmware for the middle boxes that doesn't suffer from the crash strike.
Yeah, it's just to deploy the Windows update.
Yeah.
That would be deeply depressing. But realistic.
Yeah, but realistic. Okay, wait. I feel like we need to pump some stats and like speed up this explanation. Otherwise, we aren't going to get to the new stuff.
Right. Yeah. Okay, I'll speed through. I mean,
it's been good so far. It's just well, this is ending up being like a general purpose educational stream, which probably is good because it makes it approachable for a big audience.
Mm-hmm.
Are a big audience interested? No.
They will be. They absolutely will be. You're doing CGI for this, right? The CGI diagrams. That's on the cards.
Maybe I'll have to talk to Sander. Maybe he'll be.
Yeah, he'll open up Blender.
Yeah. Well, he has to
3ds
listen
Max.
first and get really excited about it. Then maybe he could.
Oh, get really angry about the noise gating and the compression.
Yeah.
Yeah. So the thing I want to point out here is that even if this packet number 4 arrived in time, and got received, because this is in the OS, we cannot see what's in this buffer. Like I said, and even if this packet, no matter how the packet resend behavior works, like whatever packets arrived, however many packets got in, even if the TCP packet headers had like, IAC number 4 and 5 and 3 and 2 and 7, but send me the other ones. Even if we had all that, because this buffer is not exposed to the application still doesn't receive anything in the interim until the entire contiguity of packets in the stream has arrived and is available. And I want to repeat that. Even if TCP had a really good resend scheme and like a really complex resend scheme for like getting lots of the packet or like having lots of information about what packets are received, because we don't have insight into this buffer, one single missed packet will delay the reception of everything after it from the perspective of the application until that one packet is received. And so even with a good protocol, this idea that you have a stream, a quote-unquote stream, and your entire connection to this server is like one linear line of bytes is really, really, really bad for latency.
Yeah.
And in cases of any modern practical scenario where you want to send data over the internet.
Right.
And that
any
includes
case where there is
every
packet
web
loss.
connection.
Any case where there is packet loss, and of course that's all connections because we're aiming to have some amount of packet loss to know what the connection limit is.
Yeah, you will just have this, what we call head of line blocking.
And does Quick solve this a lot? I know Quick basically says, okay, we're going to not have this. We're going to move the stream up a bit so we can have multiple streams. And there's still head of line blocking, but on that stream, is my understanding.
Yeah, exactly. Quick does multiplexing, which is just multiple streams, which is really good because in the modern web, what ends up happening is that you issue multiple web requests. Like you send the TXT file, but then your browser will automatically send a request for the favicon Because remember those things, little icons on the tab, that's an automatic request. You don't ask for that. It's not even in the JavaScript or the HTML. It's just automatic. So you're going to get at least that. And then you're going to get like, if you have an image,
and we would talk about this later, but once the HTML document arrives, it's not a serialized file format with all the stuff in it. No, it's a text file with nothing that's needed actually to display it. So what we immediately do is we pass the text file, figure out, I need this image, this other thing.
You incrementally parse the text file because you don't have it all yet, but you still want to issue the new requests.
Right. Yeah, and then we start sending all kinds of new requests, and presumably most of these go to the original server. Do we keep our one TCP connection and keep doing HTTP requests on that one connection?
That would be the reasonable thing to do. As far as I understand, with HTTP 1 and like 1.1, like no, you issue a new HTTP request for every file that you want to get from the server. So like if the HTML has an image and it has a script, which is JavaScript, then these are both going to be separate, independent TCP streams that have an HTTP GET request in them. I think this might have changed with HTTP 2, but I think actually no. HTTP 3 is quick. So HTTP 3 is like what, like I said, the Google Chrome on the Google server is very likely going to do. But like HTTP 1.0, each of these were an independent thing. And that's why you can open a web page and you see the text and then you see the like JPEG load line by line scrolling down. And like maybe the style sheet doesn't load first. And so you see everything in like plain Times New Roman for like 10 seconds with a white background. And then it like pops in.
Yeah, the layout.
And it renders the actual layout.
Well, all the JavaScript, the site is very JavaScript heavy, and so what we get is some like loose approximation of the site, and then the script kicks in afterwards and like
shuffles. And it starts animating and floating around, and everything moves. Yeah.
Yeah. Oh yes, and this is we should mention this. This is the source of the extremely frustrating. We've all experienced this. I go to web page, I see button I should press. I, on my phone, go to press I start moving my hand, but before my finger has touched the screen, some new thing got loaded in and the layout shifted downwards. So, like, you missed the button because the button moved before you had time to press it. And so for the ads and stuff, that's a common one. And so you have to be in this paranoid state of, I pressed the website. I can see the website. I can see the button I want to press, but I will wait just in case it decides to move so that I don't make a mistake. And then you're actually running like a timeout, a human timeout in your head of like, well, after this amount of time, I decide that nothing more is going to arrive. So I press the button.
Yeah, surely nothing will arrive. I'm even seeing this now in like non-web stuff. This has become pervasive in like non-web stuff where they think this is an okay design like pattern, because Apple added on their iPhones a context menu for photos that like runs an ML algorithm on like image recognition and face recognition and text recognition that then has a delay on it and then pops up an extra context menu item so that when you're in the context menu for the photo, you try to hit like save, and then the context menu will add another item in the bar because there's a delay.
Yeah, that's horrible. If you do that, that's okay to have something that's lazy loaded, but then you have to reserve the space already and like have some kind of spinning guy that's like, hey, this is loading, and then don't move anything in the layout when that pops in.
Yeah, it's terrible. And I think the reason they don't do that is probably just because like there's a possibility that the ML will fail and like not find anything in the image, and so they decided they're like, oh, we'll just only show it up if something could be detected. But in that case, it's just like I would rather you don't show a context menu or you show an empty context menu until I have the completion. I don't want
just do a
bad
slightly too
interactions
big box that says we couldn't find anything in this image.
Yeah, or just literally just put nothing. Like you just have a gap. Anything would be better than what they have. So yeah, but yeah, you definitely get that on the web as well. You can get those web apps that hook the right click. So when you try to click on something, you have the like custom rounded corners context menu that like has a spinning bar for a while, and like it doesn't work properly, and you can't select the text.
Yeah, they're like in Discord, you start scrolling, and like it's not loaded.
Yeah.
Right. Like
that's really bad.
Okay. So we got ahead of line blocking. Maybe we can accelerate to the encryption scheme, because a lot of what I have to suggest, well, I think we'll be talking a lot about encryption later. So we should understand the HTTPS encryption system. Yeah.
So you send all this, you query to request an upgrade. I'm going to remove a lot of this because a lot of this doesn't a lot of the upgrade request isn't necessarily required in the case of like a more modern connection. So we'll just presume that we're just in a more regular scenario, real world scenario. If you're lucky, if you're regularly lucky. So the first thing the client's going to do after they establish the TCP connection is that they're going to want to establish an encrypted connection. Because again, all that data that was getting sent to HTTP was just packets over the internet, and anyone could just look at that and be like, hey, this guy is looking for a certain thing.
And in the beginning that was probably fine because it was, I'm looking for technical documents at CERN or whatever institution. Yeah. So it's like not that important. And everything was public access anyway, so you could have just gotten that information yourself.
Yeah, exactly. There was the concept of like private data. I mean, there might have been, but I think that was later on. But yeah, you notably the domain name is again not part of this. Domain name happens beforehand. So if you have like secrets.com, that's going over the DNS system, which is like usually not encrypted, which means anyone could just look at that. But that's a separate conversation, I guess. Because we were assuming we already have our IP address. So I'm going to try and get this right the first time. The client starts by saying, I want to do, let's assume it's TLS and not SSL. Or TLS 1.
Well, those are basically the same thing, right?
Yeah. It's like we send I think it's called the client hello. But the client is like, hello, server. I'm a client. You don't know who I am. I don't exactly know who you are. I just know that you're I know that you're a server on this domain name. I want to establish an encrypted connection with you. And I want to get that ball rolling. And this is, of course, again, I want to point out this is gonna be a packet that's sort of inside the TCP stream connection. So like, it'll be the first bytes of the stream.
Yeah. And notably as well, these are packets that get delivered in our stream, which is delivered in packets. So we've like undone our stream abstraction here already.
Yes, yeah, they're TLS like packets that are considered to be, they're like individuated, but they're still on the TCP stream, so they like get sent reliably. But they could get sent, you could send it again, and like so you could send it again. You can send any TLS, but like you can choose how you're gonna do if you establish a protocol, and you have packets in the protocol, you can send packets again, right? So if you send a packet and then you send it again on TCP, this is going to get resent until it's arrived on the server, and then this is also going to get resent until it's arrived on the server. So if you do resending on TCP, it's like you're actually guaranteeing like a double of that is going to come through. And then the application will see that a double of that comes through. And there's uses for that, but just be aware of that.
Right, yeah, that's also a failure mode, right? If you stack two reliable connections on each other, that are obviously doing this reliability via timeout, is you're sort of that is guaranteed to eventually explode and you get no data transmission.
Yeah, because you're doing resend to resend to resend to resend. Yeah, that's a rough scenario that you want to avoid. I'm pretty sure that's what WebSockets are, but I could be wrong about that. I think it might be just UDP over TCP, approximately. No, I think WebSockets are actually TCP over TCP, and I think they just don't have resend because you don't need resend.
Right.
Like I think they avoid the explosion, but they don't. They're still kind of a joke. So the client hello arrives or doesn't, in which case it gets resent and arrives on the server. This is assuming like a stable TCP connection. I'm going to remove the TLS 1 now. I'm just going to call it TLS. The server says, and acknowledgements will be being sent implicitly here on the TCP connection. That's normal. The server is going to send the server hello, and that's going to contain, I know at least one thing it's going to contain is what is my certificate. And what the certificate is basically just we want some way for the server to not just encrypt data, but also authenticate that it is like
it says
legit.
Yeah, we actually, and that's for man in the middle, right? So back to the coffee shop, Starbucks example. We want to prevent Starbucks by saying, well, I connect to google.com. I need some way of knowing cryptographically that I did in fact get to crypto or google.com that I intended, and not the guy in the Starbucks with his laptop that says he's google.com.
Yeah, exactly. And so this certificate will usually include the domain name in it. Or it will... Yeah, the domain will be involved in the certificate. So that like google.com domain has an ability to be authenticated. I don't remember if the domain is in the certificate or if the certificate, like when you go to check, when you sign it.
Well, I'm pretty sure the scheme for these originally was... Okay, so the certificates, the way we do this is... maybe we should explain signing.
Yeah, well, yeah.
Well, okay, basically we have this thing in cryptography, which is we have a key pair with a public and a private key. And basically the signature, this is actually, for people who learn RSA, they think of this as encryption. But for signatures is actually a wider topic. So we should just say that, like, hey, I can create a signature with the private key, and somebody with the public key can verify that signature. We don't use this for communication when we're doing signatures. We just use this to verify that indeed whomever has access to the private key, which is you because you don't share the private key, that we can verify that the information originated from you, or that you did the signature. In a way, think of it like a normal signature on paper, but it actually works as opposed to, not working or like being really easy to cheat.
Yeah.
So what we do is that we have some central authority in the world that we decided we trust. I think.
Wait. Before you get into that, can I just really quick cover how public and private keys work? I can do it really fast. So and for signing, so the thing about a public key is that it's a number. It's like just some big number, and other people, not the guy who has the private key, but other people, the only thing they can do with the public key is they can encrypt data. This is going to be like RSA or like asymmetric encryption. This is different from like Diffie-Hellman. So
the reason I'm hesitant about, look, I just want to preface this with, this explanation actually is entirely wrong when we get to post-quantum encryption later. But we'll do the RSA because that's the classic.
Yeah, I'll just run it quick because again, this is just going to be rough to give people who are completely noobs like a basic idea of what's going on and why this is useful. So, the other people can encrypt some data, like hello, using the public key, and then it becomes like a jumble of numbers. And then the only way you can get anything sensible out of this jumble of numbers is if the guy with the private key uses the private key to decrypt it, and then they get the hello back. And there's padding and other stuff that I won't get into. Yeah. And the way signing works, at least with RSA, is that it's a little bit funny. Given some public message like I'm cool or whatever, like something that's public and available and everyone can understand, I want to sign it. I want to say, hey, the guy that owns this private key actually knows this, or actually is the one who wrote this, or
approves of this message,
confirmed it. Yeah, approves of this message. What I do is I hash it. I won't explain what a hash is, but it just turns it into like a smaller, consistent, like unique, like sort of identifier for this string, and then does a decryption of this nonsense number into another nonsense number.
It is an encryption,
but this
RSA doesn't care. RSA is the same both ways, so it's an encryption.
Sure, yeah. But what's important is that it's only reversible through the public key. So everyone else can get this new jumble of numbers, and when they encrypt, or I guess decrypt, this signature back into the hash, or when they try to do it, it will turn into the hash.
Yeah.
And they also know this hash function, so they can run it on this string to get the hash function. Yeah. And so they can verify, like, given this string and this signature, I can see that it determines this hash, and that when I run the public key on this signature, I get the hash, which means
and I think actually
only the guy who had the private key.
I think actually you send both normally. You actually send here's the hash and message. Here's my jumbled hash, and also you might send here's who I am, here's my public key in case you didn't know.
Yeah, and that's like that's a very good. Complete. I think that's like how PGP works or whatever. It's like, here's the email, here's my public key, here's the hash of this email, and then here's the hash that's been encoded with my private key as proof that I have the private key that is associated with this public key.
Yeah.
So here's who I am, here's my message, here's my signature.
Yes.
And so that's a very robust way, using RSA specifically to do signatures. Again, this changes with, it might change with elliptic curve, I don't know, and it definitely changes with post.
Elliptic curve is also
you know more about that than me.
Elliptic curve is also symmetrical, and so they use elliptic
asymmetrical?
curve. Oh, sorry. Well, I mean asymmetrical. I mean in that you can go both ways, public and private. Like.
Yeah. Okay.
And so is, elliptic curve Diffie-Hellman is the same kind of principle. Because I think, elliptic curve is like the same primitive that you build. It's like replacing modulo canting with elliptic curves. And then they could do all the same things on top. There are other non-quantum secure encryption schemes that are more funky and that aren't reversible in the same way. Like for signatures and stuff.
Yeah, exactly.
One aspect here that we haven't, or for these signatures, actually, there's a flaw in that there's only one signature for one set of data, and that's actually bad. And so you have this thing called a nonce, which you add, which is we'll just add some randomness to the message. Or
Yeah.
we'll add some randomness in the signature that you have to include with the message to get the hash. Yeah, but that's only part of the signature. Now, I'm not sure. There are other encryption schemes that you can actually generate many. I'm not sure if they're non-spaced or not. My knowledge ends there. Anyway, with this certificate, basically the server hello will contain a certificate, and it will say something like, I am pets.com. And then it'll be signed by the central Uber authority. So what we do is we basically say there's like the Ministry of Names of certificates, which we trust and have the key for, that will sign the certificate for pets.com. And then they present us with this certificate, a little bit like some kind of ID card or passport that's been given to you by your nation. And it used to be back in the day that you could buy you had to buy these, actually. They were like commercially given out.
Yeah. The same way the domain names are given out. I think they were usually associated. They were like similar services as the domain services.
Yeah. So you buy a certificate for your website from some company. Then at some point we decided that this is bad for hobbyists and stuff. And so now we have something called Let's Encrypt, which does some kind of... They I think, charitably give out certificates with something like they connect to your server and verify that you are in fact the person who has this server, and then they give you that certificate. There's some kind of process there. Anyway, so we basically
get certificate authority.
Yeah. So in theory, this certificate authority is like governments or ICANN or someone. In practice, it's Google. Yeah, well, in practice, it's Google. Because I think Google is not supposed to be a certificate authority. But in practice, Microsoft and Google are certificate authorities. Yeah. Or at least they're the ones who install the certificates on your machine. So they can actually...
Because I want to clarify, the client is aware of this authority because the client knows this authority's public key. So that when a certificate is received, we can verify this signature, this signed certificate. It can verify the signature given this public key, that this server is who they say it is, and that is the source of the trust that the client establishes with the server. The client is like, okay, this server is who they say it is because the authority gave me a signature that says they were who I say it was. If I don't have this authority, if I have some other authority that I trust, I don't trust this certificate, or I don't know whether to trust this certificate.
Yeah.
And so the way the client gets the authority is, well, you download it with Google Chrome, or like it's installed on Microsoft Windows operating system.
Yeah, and actually
like this a public key that just comes with your laptop.
And in terms of software complexity, this is where they really shit the bed. Like how certificates are installed on your Linux box, for example, is that actually there's just a big directory on in /user/share somewhere that just has these, and then you call into... So we've already entered the realm where like nobody implementing TLS from scratch is very non-trivial, is my understanding. And so it's like, oh, you have to link OpenSSL, and then OpenSSL will like dig through all these files on your file system to it's this whole network of certificates and stuff, and it will use that to verify this certificate that came in.
Yeah, I want to point out that this is actually a nested hierarchy of authorities. So you have these authorities that then like delegate more authority to other authorities. And the way you trust these authorities, you might not even actually know about these authorities on your computer, these sub-authorities, but what they are is that they are signed by a higher authority.
Yeah.
and you trust the chain of signing because you kind of can.
Yeah, and then you get to the root
and
authority,
they
which is
ultimately
which are these international
Yeah.
bodies. Except that the only
Yeah.
reason you trust them is because you received them from Google or from Microsoft. And so actually Google and Microsoft in practice are higher up in the chain than the international authority that gives them their certificates.
Yeah, exactly. Ray, I see what you're saying. Like, even if someone else has the root certificate, you're saying Google gave you their root certificate, so it's really
they
Google
could have
sort of
given
controlling
you a fake different certificate.
Yeah. And by the way, there's nothing mandating that. I think there's nothing mandating that Google actually delivers you a web browser that follows the Microsoft operating system APIs in order to do web connections. Like, Google could just start sending out its own packets without trusting the machine's certificates. Yeah, they probably do.
I bet they actually do that.
Yeah, possibly. Of course, there's
they might have a backup.
Microsoft can detect that.
Yeah, they might have a backup where they go to the system and to their own store.
Yeah, and then double check them and say some laptop manufacturer install the root certificate.
Well,
we don't agree
because
with
that's
on
supported.
Your laptop.
You're supposed to be able to do that. That's actually expected functionality, is the ability to install new certificates that Google doesn't know about on your machine.
Yeah. Yeah,
and to
decide not to obey them.
Yeah. But
in Google Chrome, I mean, sorry.
Right.
Specifically,
they're supposed to let you.
Firefox will do its own thing.
Yeah, they're supposed to let you just decide to trust this new certificate. But I don't know if anybody does that.
Yeah.
Anyway, this is a very long way of saying what? That we get the server hello, and it contains the certificate.
Yeah.
And then what?
And by the way, a little nitpick here is that, of course, both of these are going to be what is my version number and what kind of encryption is allowed. What am I actually capable of? Because of course, there's not just one encryption scheme. There's many.
Yeah, they have to agree.
So they both have to do the common denominator between what they both support when they establish a connection.
Yeah.
But
to foreshadow a little bit, my scheme relies on the DNS system having done a lot of this work ahead of time, so the client already knows about what things the server supports, and therefore that stuff can sort of be implicit.
Yeah, the secret here is that there's actually more to this timeline backwards, where in order to even know what IP address you had to connect to, you had to touch some other server that was a DNS server to figure out what does pets.com actually map to, and then he tells you what pets.com maps to, and then you get the IP address, and then you can do a connection.
Yeah, and in practice, that's
your
ISP.
I don't know how.
Or Cloudflare.
Yeah, so it's like Comcast or whatever.
Yeah, very American example. Can we get Telia instead? Can we make this a regional example?
Yeah. We can get Telia. Telia?
Yeah, Telia, like that.
Yeah. So we're gonna get a packet that tells us. Yeah, we have room. We're gonna have access to we're not gonna, given DNS, we don't have anything except the IP address from the name, or we have some other stuff. We have some records that say
that's more for email. For email, they threw a bunch of more crap into DNS.
Yeah.
But yeah.
And then there's a little bit of name remapping you can do on subdomains and stuff, but it's not.
Yeah, there's also reverse DNS,
basically which just strings.
There's reverse DNS, which is you can query the DNS system backwards, say which name does this IP address map to, and you maybe can decide that, hey, if doing the reverse request does maps to something different, then maybe you think that's sus. But in practice, you can't do that because that's not consistently set up because people want different setups.
Yeah. So, I mean, given that name and given you're going to have to rely on the server to tell you the certificate, and then you have this root authority system that maps the name and the public key to the signature, or like given the name and given the domain name and the signature, you can determine whether or not the authority signed it.
Yeah. And part of the reasoning here is that, or maybe this is actually not done, but I'm pretty sure we double check back. We're basically checking to make sure that this information agrees with the DNS as well, right? We intended to go to pets.com. If we receive a certificate for, horses.com, we have, questions.
We've got a problem.
Yeah.
Especially if we try to go to meat.com and we get horses.com. I would be a little bit suspicious of that, but some people are. So the important thing here is that the name and the server are authenticated with respect to each other and with respect to the authority. So all really the authority tells you is like it signs that like, hey, this is legitimately what a server from pets.com. And then I think maybe it also says like what is the like name of the corporation that runs pets.com.
Yeah, exactly. There's some stuff in there
There's
which
like a legal
mattered.
entity.
Yeah, which mattered when they were doing these commercial certificates, and then now is completely undermined by the free certificates.
Yeah. Like some guy will register a domain name that's like the legal entity is like Bozo Software LLC or whatever, and then
you can find thousands, I bet, of certificates that claim to be Google Inc. or like Google with an extra O.com.
Google.com. Yeah. So you get some of that. So really, the thing you rely on is just the correspondence between domain names and the server, which, by the way, is why, like, when you get spam emails and spam text messages, you'll get, like, pets.com.top or something that looks close enough for grandma to think that it's pets.com. And this is, like, a completely secure HTTPS connection because it's actually someone registered the petscom.top domain name, and they got a signed certificate for petscom.com. Even though it's actually linking
everything
to, like,
is green.
Yeah, everything is green on the HTTPS connection because it was genuinely signed correctly. Even though this is a phishing link that will like scam your grandma out of her credit card information.
Yeah, and I guess that's kind of the solution they wanted to fix with the commercial certificates. But I actually think it was the right decision not to have those because then the internet becomes like the TV, right? It's like only approved servers can be connected to.
Yeah, exactly.
Which, look, maybe is the appropriate thing for your grandma, but
maybe your grandma should only be watching TV. Not mine. Mine's a pro.
Yeah, or like, only contact approved services.
Yeah. So we have this mapping, and so the client's going to be like, okay, everything's above board. The name is mapped to the certificate. The certificate is authorized. And so the next step, I think semantically in the TLS spec, I think these are specified to be two separate packets, but I think they like almost always come together as one. It's just a big bundle. And again, we don't have to worry about like the packet being too big or anything because this is happening over TCP. So it's not subject to the like size requirements that packets are usually subject to because again, we have this reliable layer prevents like drops from like affecting the connection. Or it does resending and it does fragmentation on the TCP layer. So now the client starts doing kind of the important encryption stuff, where it says like, okay, you're valid, that's good. It's time to, what is it? It's time for me, as a client, I'm not going to authorize myself. I don't have a certificate. I'm just a guy. I'm just a rando. Yeah. Because that's the model that we decided on. We decided it's not a two-way thing. We don't have an equal authority position here. The server is supposed to be like, I don't trust you, server. You got to verify yourself. The server's just like, okay, you're just a bunch of guys. Like, just come at me, bro. Do whatever you want.
Yeah. Which honestly, I think is the correct approach. Because the clients are often not permanently on the internet, they're like connecting out from NAT. They're not turned on the whole time. Like, it doesn't make sense for them to receive
dude
any
on his
connections.
Phone going to like twitter.com and he's not signed in. Well, there's nothing to authorize anyway. Like, it's just a public website that is just displaying public information to a user who's not logged in. There's no credentials to be authenticated. I just want to like collect public information.
And while we don't have a good system for that on the existing internet, I think I have a decent system for that. Even in my scheme, there's no reason to do that on initial connection. Right? Like you can do. It's actually fine to authenticate the user as a separate step, because we just first want an encrypted communication channel, so we have a persistent. We know that we're talking to the same client throughout this entire session.
Right. Yeah. So one thing that can happen. So I'm not on the exact details of the encryption here, but so the client, given that they're not going to be authenticating, they still want to establish an encrypted connection. So one important part of that is going to be there's a thing called symmetric encryption, which is like Diffie-Hellman. I'm skipping ahead a little bit because I want to motivate this.
Okay, sure.
Yeah, Diffie-Hellman
is a key exchange. It's how we establish.
Yeah, it's a key exchange protocol for establishing a symmetric key.
The actual for symmetric encryption, everybody uses something called I'm blanking on it now.
DSA?
AES.
You see DSA? Oh, AES. Okay. Yeah.
And AES is actually good. The people did a very good job on AES. Everybody uses AES. AES is awesome.
Yeah. The symmetric encryption can like be made to run fast. This is happening on Intel chips really quick with built-in instructions.
Yeah. And AES actually is fundamental. Like your mental model of it can be just the encryption you did in school of like Caesar ciphers or something, where it's basically like I take my message and I scramble it in some way, and then the guy on the other end can do the reverse scrambling. And we have this key, which is this 128-bit number or a 256-bit number, which describes the process of how we shuffle it and how we then unshuffle it.
Yeah. I sort of jumped ahead. Diffie-Hellman is not the symmetric encryption method. It's one of multiple protocols for establishing this key, which is like a shared secret. It's like a number that the client has and the server has, but other people don't know. You can do Diffie-Hellman in the clear, like talking publicly to another guy, but you don't know, you can't use Diffie-Hellman to like verify that other guy is who you think it is, which is why we do all this authentication, certificates, and asymmetric encryption.
Yeah, because there could be somebody in the middle, a so-called man in the middle. Or I guess
Yeah, just imagine that there's like a guy, you're doing all these TCP and TLS packets, but there's like the server you think you're talking to was actually like over here. It's some other guy, and this guy is shuffling, like relaying all the packets back and forth, except like ingesting his own, like replacing the certificates with his own and everything, or replacing like other stuff with his own, and then he could like sniff your connection without you even knowing. This certificate. The signed certificate allows you to avoid that, because what you're going to do is you do the key exchange protocol. We're going to encrypt this key exchange protocol so that the man in the middle doesn't know what the shared secret ends up being, or like he doesn't even know what you expect. Basically, when you encrypt the key exchange protocol, you can establish a shared secret that isn't even in the clear, so there is no way for a man in the middle to get access to it. So he can't like establish his own Diffie-Hellman with you and then separately do a Diffie-Hellman with the server, because the only people that can read the Diffie-Hellman on the server was everyone who has access to authority to sign the certificate. And actually, in fact, it's not just the certificate. The server ends up also generating its own public key. I don't know how often this happens. It could be per session, per connection, or it could be like every day, every week, or something. Yeah, it would be expensive to do it every session. Although I think it would be possible, but it'd just be expensive. But basically, the server just has sort of authority to like decide when it's going to generate a new public key. But that public key is also going to be
as does the client. Signed. The client, I think, generates when it connects, or at least
yes.
It kind of doesn't matter that much, but it's
Yeah, and this is why I was motivating the asymmetric encryption first, because we're going to get to the key exchange. So that the client is going to be the client when it's building this is like the meat. The client is going to be putting in the next packet. It's going to be putting in its public key to say like, okay, here's how you're going to address me and like encrypt messages to me. And then given the server's public key, it's going to encrypt. Actually,
is that true?
It can
I
encrypt.
think the difference is here TLS 1.2 and 1.3. For 1.3, they managed to shave a round trip off, I believe. So I think it might be that in 1.2 we now send our public key.
Right, yeah.
Along with encrypted data, and then the server sends back it's part of the Diffie-Hellman handshake, encrypted with that public key, like you're drawing now, right? So we do this exchange. No, sorry, wait. So TLS 1.2 would have been like 3 handshakes, and then it might. I can't remember if it's 2 or 3. It might be that TLS 1.3 got this down to 1 handshake.
Yeah. So let me see.
Because they include stuff ahead of time in the initial client hello that allows them to accelerate this process.
Yeah. I think I have it. Hold on. I'm consulting the documentation. I'm RTFMing, as all Linux people should. Yeah. So I think what happens is you send the public key. Server says like, okay, given your public key, I can do my side of the Diffie-Hellman, and that's encrypted with this public key. So it can only be seen by the client. And then the client does, here's my side of the Diffie-Hellman with given your public key and encrypted with your public key. And then by this point, they both have a shared secret, because this is how Diffie-Hellman works. This is TLS 1.2, I'm pretty sure. And now here they're going to start sending packets to each other using only the Diffie-Hellman public key, or Diffie-Hellman, shared secret. They don't need to use each other's public key or private key, which makes it the encrypted communication faster, because it's faster to do AES than it is to do like asymmetric encryption. And so this is like 1, 2, 3, 4, 5, I think, round trips or something. Whereas, you can.
You also have to worry about key leakage, right? In that we do this both for speed. Symmetric is just way faster. We also do it to avoid leaking. If you use asymmetric keys too much, you basically over time leak information. Like if somebody can collect over a long period of time all this encryption stuff you've been doing with the asymmetric keys, the asymmetric keys will slowly leak like into this data, and you can do computation to figure out what the private key is and then pretend to be the server, which isn't good. So we want to get onto symmetric encryption for the session as quickly as possible.
Yeah. And then, with Diffie-Hellman, you can also cycle your Diffie-Hellman keys and do the Diffie-Hellman encrypted under the previous Diffie-Hellman, or just encrypted under the asymmetric keys if you want to be really safe. And then that'll let you establish a new Diffie-Hellman over and over, so that most of your messages are always getting sort of refreshed with more security. Again, in a post-quantum world, that's not really available. It's
actually the Diffie-Hellman
post-quantum
ceases to exist, but we'll get to that later.
Yeah. So this is that what I described. I'm actually pretty sure this is not even TLS 1.2. This is TLS 1.3, because this is relatively reasonable. You have hello, public key, Diffie-Hellman.
No, I think what they did is...
The thing that I left out is cipher-like determination. So
was
you
that
start
an
with the
extra
client
step
hello.
before?
Yes, in TLS 1.2, it's like, okay, here's my certificate. Okay, I'm authorized now. And now it's like, okay, I'm now determining, I'm going to tell you what is my encryption scheme. Like, what encryption scheme am I using? So it's called the cipher spec.
Mm-hmm. Yeah.
Here's and they put the certificate in this encryption scheme one. Here's my certificate. So the server hello just tells you what is my like initial cipher suite. Cipher suites are complicated. I don't really know that much about cipher suites.
Well, the cipher suite is just like we have a range of options exactly on what encryption we could be doing.
Yeah.
And then the client chooses?
Yeah, because the client and server both have to agree on which ones are available. So we send the encryption scheme. I don't know if the certificate and the encryption scheme are sent in separate packets. It's kind of not that material because they could get buffered up or whatever. And then the server says, the client says, like, okay, now that you've told me the hello and the encryption scheme and the certificate, I know who you are. I can establish who I trust you. Given your available encryption schemes, I'm going to tell you what's my available encryption schemes and what that's it. Yeah, we don't need to send a certificate. So then we know, like, okay, here's my encryption scheme. Now we can do Diffie-Hellman, and now I can do Diffie-Hellman. And so I think that's one extra round trip, because it's hello, here's my encryption scheme, here's my encryption scheme, here's my Diffie-Hellman, here's my Diffie-Hellman. So that's 1, 2, 3, 4, 5, 6.
Well, okay, so if we do the
like
ping time, if we do count round trips here, how much latency have we got? we said 150.
Ignoring the DNS.
So we have 150
150
on the piece. Yeah.
150.
The first hello, second hello.
150. Second 150, 150, and then half. I think it's. Now,
You said
again, don't
old
quote me on
TLS
this,
was 3 round trips. Modern
yeah,
TLS
old
is
TLS
2
was.
round trips.
Yes, that's correct. I think I'm leaving one thing out here. I'm leaving one packet out here, but the details are like, this is
Right.
obsolete.
So we got 3 to 4 round trips, which would put us at.
Yeah, we've got just TLS is 3 round trips. 1, 2, 3. And then the TCP is another round trip.
Well,
half,
I know
but the half can be ignored.
new TLS is 2 round trips. So if we're going to give the benefit of the best case, 2 round trips plus
best
1
case
initial,
scenario,
we have 3.
We have, best case scenario, we have TCP, 1 round trip, TLS, 2 round trips. So like ignore this. This diagram's a little bit messy, but you still get it. TCP plus TLS1, TLS2. So that's 3 round trips total, not including DNS, because you have to, and that's 150 multiplied by 3. So that's 450 milliseconds to start sending data.
Yeah, which would then be your like actual HTTP request in the web.
Yeah, which would then be the beginning HTTP GET, which says like get me the index, and then this will be an HTML file that has an IMG file, like an image, and a script that says like, oh, go do another TLS connection to set up the next GET request, and the next GET request, and these can be parallelized, but they're still those needed to be
okay. So, but we've gotten the like
first.
Approximate 1 second to load a web page though. Because we had 1, 2, 3, and then 4 round trips at minimum, and then if our ping time is 150 milliseconds, well, that's almost a second.
Yeah.
Because we've got 600. That's about the half second, right? And then we stack the So actually, what I'm surprised is actually how 600 milliseconds is still like not that perceptible. So there's like many more layers of junk they added.
Yes.
And
TLS
more and
is
more
not
round
even
trips.
the bad part of it. Like really, is like, or it's the least of your problems when you're working on the web.
Right. Yeah.
Where like you have all these other causes of problems.
Well, yeah,
usually
and then
as
like soon as you go
JavaScript running,
as soon as you go to a
ends
different
up delaying
server, we have to do a new TLS handshake and a new TCP connection.
Yeah, we can give the benefit of the doubt to the like successive requests on the HTTP gets that come after. Like if you have an image, there's definitely optimizations that can be done in the modern day. I mean, this is before Quick. I'm not going to talk before we talk about Quick, or if we do. Just now that you know like the Cypher suite's available, and if you're using TLS 1.2 or 1.3, there's probably something you can do to start issuing the HTTP request for the image before, like without having to do as much.
Yeah. Do you know how video streaming works? Like how they had to invent video streaming on the web in the early 2000s?
I'm pretty sure it's just you send a request for like a range of bytes in the file, and that's an HTTP request that gets sent.
What they have is already like the file formats. Video formats are so wild because you have this difference between containers and then the actual codec. But then the codecs are split up into these packets. Again, we have packets. It's a packetized thing, not a byte stream. So I guess they're called frames, which is different from like iframes and stuff. Anyway, you have this thing where the container format already has like, here's a chunk, and here's a chunk, and here's a chunk, and these are like meant to be delivered. They're processed discretely by the video decoder. And so what they do is they just say like, hey, let's take some number of these chunks and put them in and request them over HTTP. So like a video stream is that your browser or whatever is just making like continuous fresh HTTP requests for new chunks of the video stream. And that would get really bad if they had to do this handshake over and over again. So I'm pretty sure they reuse the TLS handshake.
Yeah. Also, one detail that I probably should have gotten right is that Diffie-Hellman, I diagrammed the Diffie-Hellman as happening at the bottom here at the end. But actually, Diffie-Hellman can happen at the top in the hello, because you do authentication anyway, just when you send the certificates. So you do Diffie-Hellman to like encrypt the hellos and the like choice of encryption scheme and the certificate, just symmetrically. And then, I mean, you have the choice if you want to do Diffie-Hellman again, although I don't think it's necessary. Because again, the fact that you have the certificate breaks any attempts to do man in the middle, whether or not you do Diffie-Hellman before or after encryption. But yeah, if you wanted like a more robust thing or a more secure thing, you could do Diffie-Hellman on the hellos with a pre-decided scheme, and then certificate authentication, and then asymmetrically encrypted key exchange inside the encrypted connection, and then you have like a new key.
right. All the layers.
Yeah. You want more and more layers of encryption.
Yeah.
Kind of.
Okay.
Well, if you're Signal, you do.
Yeah.
But yeah.
If let's say, okay, at this point we've delivered basically our text document, right? Because what comes after this is the HTTP request for the text document, which was the original North Star of our investigation.
Yeah. In fact, actually, there's one more round trip, right? Which is the request and then the HTTP response, which I didn't talk about. But then the HTTP response just has the text file in it, which is,
which will be delivered in plain text.
World.
Well, I mean, it's a text file, so it would always be plain
as
text.
a text file.
It's not compressed. A
text file that is, not compressed, but it is encrypted because it's on the encrypted channel. So it's not really. I mean, it's plain text file on a plain text connection that is in an encrypted connection, like an encrypted layer. So it's encrypted, and then the client decrypts it. So you can also in the HTTP headers you can ask for a gzip compression, and then the HTTP response can be gzipped. But that's again it's an optional feature that like is usually happens, and like a lot of people rely on it so that they can allow their JSON to be more goopy, to be more bloated. But again, everything here is like half of the things I described are like optional extensions. HTTPS is an optional extension to HTTP.
Well, it's an optional extension that is layers. Mandatory.
Yeah, you're allowed to do anything else as long as it's HTTPS.
Yeah. I was just gonna say we can just retrospectively look back and say, wow, gee, what if we wanted to do unreliable transport at the end of this process? Could we do that?
There's no well, fundamentally, the entire premise is that your connection is happening over TCP. All of this that I've described is happening on one TCP stream.
Yep.
Which means, by the way, you can't multiplex this TLS connection on top of the TCP stream, because if you send a packet that says like, oh, channel number 1 has packet number 2, and then you send another packet that says channel number 2 has packet number 5, those are going to come in order on the TCP stream. So you can't multiplex on TCP, as far as I understand. Or you can't multiplex in a way that avoids head of line blocking. So there's no benefit to multiplexing, really.
And we absolutely can't just drop intentionally or like not selectively resend stuff. Because we did this like comp sci abstraction of saying like, hey, look, we have one byte stream and then we have another byte stream that's like inside of the byte. It's like layers of byte streams that are happening.
Yeah.
and that just limits you. So let's should we then go talk about Quick briefly and some of the problems that it solves on this? I know you care about
we can do
Quick to some extent.
Yeah, I think it's worth mentioning. We'll do a quick review of Quick. I just want to erase this real quick. I commend them on the branding. It was a really good.
With of course the special spelling to make it
maneuver.
searchable.
Yes, they have good SEO, decent enough SEO on that. And Quick is actually a pretty interesting story. There's a few interesting details, or actually there's like one interesting detail I know that I'll get it. It's about UDP port 80. Quick, for anyone who doesn't know, Quick is basically a protocol designed by Google to basically just replace all of this. And it's to basically, Google decided that the world would use HTTP3 and Quick would be HTTP3. There wasn't like a discussion to be had. It was Google decided this, right?
Actually,
you will now use Quick.
Very based. I don't think it would have happened if it had been given to like the Web Consortium.
Yeah, absolutely. So I'm just gonna make a new file here.
That's like the way most good protocols happen, or good file formats, is that somebody, like, there's no committee. Somebody centrally designs it, and then just adopts it, and then it becomes popular, and then everybody else gets on board, and then they like ratify. Some committee can rubber stamp the centrally designed protocol.
Yeah. Okay. So the way Quick works is that, good idea number one, it's not TCP. It's actually UDP. So instead of sending this UDP, instead of sending a SYN or anything, or like there's no UDP, for anyone who doesn't know, UDP is a protocol where you're just allowed to just send packets to anyone for any reason at any time. And then like they may get through and they might not get through. Your firewall can like do some stuff or do a lot of stuff to UDP packets. They can choose which ones get through, which ones don't get through. So it's not just like totally gung-ho. But
you need that for a civilized internet as well. It's like network operators need to basically be able to censor packets they think are bad actors.
Yeah, like the things that are like DDoSing or spam, or stuff like that. They're just sort of thrown away, and that also I think that can also happen with TCP, because with TCP you can like you can be a bad actor by sending the reset bit. There's a reset RST bit. And if you set that bit on a packet, you can reset someone. I think you can reset someone else's connection if you like spoof their IP. And so you could just spam reset packets at somebody to just like prevent them from connecting to the internet, or prevent a server from.
But there's the more extreme case, right? Which is you just said like 1 million SYN connection packets.
Yeah, you can also SYN flood. You can do a reset attack. You can do a SYN attack. So this UDP packet, of course, it has UDP header and whatever. But then just straight up, we start with some Quick payload. Quick is QUIC, by the way, if you want to Google it. Google the Google protocol.
It's also the name of a compiler, I just realized. Almost. No, of course it's spelled differently. Yeah, I remember. I was confused there for a second, yeah.
There's an old compiler from the 90s called QuickC, and then there's a new compiler that we are very interested in and we would love to see happen and finish called Quick, which is a C99 compiler that is like almost basically fully featured and like not very...
That we officially endorse.
Yeah, I officially endorse. Not very used yet, but like pretty robust, pretty bug-free. There's no... there's no compiler other than Quick that does like order independent declarations, I think, for C99. I could be wrong about that. Don't quote me. But, order independent declarations in C, fun thing. Everybody go buy Quick, and by which I mean go use it for free, but
throw money at the creator. That's very important.
Throw money, yes.
Yeah. That said, I actually haven't shipped any project where I was using Quick, so your mileage may vary.
I've never used Quick.
Yeah, I've bought Quick, but I haven't used it.
Right. Well, that's the way we support our known good programmers.
Yeah.
So, I think I'm gonna try and get this right.
And I should preface as well, the only reason that is because in the period that Quick has been around, I've basically not written any C programs, because I have my own language and compiler. But everything good that I know about writing compilers, I learned from the guy who made Quick.
Yeah, exactly. Everything I learned, well, almost everything I know about how to make good compilers, I learned from the guy who made Quick. I've been inspired by him. But I also learned from Per Vonsen Bitwise series. That's very, very good. And I was heavily inspired by a lot of that code for the compiler work I did. I want to point out that with TCP, the application wasn't able to send this SYN-ACK handshake. Like, again, this was, like I said in the beginning, it's Berkeley socket API stuff that's going on in order to establish that connection. There's no insight into it. Whereas with UDP, you can just send a packet, and the packet has a payload, and you can just start doing that.
The UDP basically was designed as the way a user application is allowed to just use IP without any handholding.
Yeah, exactly. Without having to use a stream.
Yeah. And also, as well,
establish a connection with a reliable
today
stream,
with modern IPv6, and we'll get to this on my design for Serenum, but today with modern IPv6, a single device is allowed to have as many IP addresses as it wants, and basically has infinite IP addresses. And that means that today you could do this thing where every program trivially has its own IP address and can do all the IP stuff that it wants, because every program is functionally its own device on the network. And that is
and on IPv6 you could multiplex your connections by just establishing multiple TCP connections from multiple IP addresses.
Right.
But I don't know how that would play with NAT. And you could kind of already do that with
as the client,
HTTP requests. You just issue multiple.
Yeah.
But of course, there's no like protocol for doing that, because like HTTP, you have to wait until you get the index web page before you can figure out what you're even asking for.
Right.
You can't like pre-establish. I guess maybe you could pre-establish multiple connections and then like wait on them for like figure out what you're going to do with them. And web browsers might even do that, because it's crazy enough.
Well, they already do this thing for IPv4, IPv6, where when you connect to a website, they connect on both, and then they see what arrives or like what goes through.
Yeah, exactly.
So you already have two, an IPv6 and an IPv4 connection to the web server.
Yeah. So, why not more?
Yeah.
Why not add more complexity? So UDP avoids that by basically saying, or Quick avoids that by basically saying, we're on UDP, so we can just send payloads immediately. So we can just send our hello as our first packet. And I don't know if the client's public key goes in the hello. Probably not. I mean, I can double check that. It's not super material, but that's immediate. There's no need to do a SYN or an ACK or There's no need to establish TCP connection because the packet will either come through or it doesn't. If the first packet doesn't go through, well, then the server has had no reason to send anything to the client, and so the client won't get anything. So the client will just send it again. The client establishes their own reliability layer by having, custom application layer resends.
Is that true? Can you use Quick to send unreliable stuff? Because I was unsure about this. My understanding was it kind of felt like at least from the public presentations they did about it, it seemed like at least their focus for the web audience was, we provide you the same stream API.
Yeah.
But now you can have many streams and they're multiplexed and they won't do header blind blocking.
Yeah, I think specifically for Quick, I don't think there's an ability to do unreliable. I mean, it would be based, but
they'd first have to discover
of UDP.
They first have to discover the ability to have UDP as a web JavaScript API first. Then they'd realize that people want to do this. And current, there's no point in them adding this to Quick because, like, what would you do it for? Like, the JavaScript can't do UDP connections.
Yeah.
Isn't that also the reason why they have the cult of being anti-UDP in the web world is because they don't trust developers to actually call the functions to do encryption. So they're like, no, everything must be TCP or something. Everything must be a byte stream because then we can make sure the byte stream is secure.
Yeah, because it's encrypted, and we don't know how to encrypt something if it's not in order.
Well, no, it's we don't trust you to call the encrypt message before you send the UDP packet. Right.
Yeah, exactly. There's a common pattern on the web where they try to establish the like really complex, high level, supposedly expressive sort of experience, and then come to understand that they needed the layers in between that they built up to get to that anyway, and then they jerry rig like a worse version of that lower layer on top of the upper layer. You have this like with like web canvas where instead they started with a document object model that has like this complicated renderer, and then they're like, we want to just like put pixels on the screen, so we'll make the web canvas API that is like an element in the document object model that's on top that lets you get a frame buffer and put pixels on.
And look, I bet that originally sounded like a good idea because it's like, the canvas is just a small part of the web page where you wanted to draw some special stuff. It's actually the minority case. Then,
Facebook Messenger comes out, and they realize they want to commandeer the entire page and not really care that much about the document object model and just render to the screen the things that they want to render at the specific places they want to render it. They don't want to be subject to CSS layouting rules when they put the mouse cursor replacement on the screen.
Of course, they still have to duplicate the content in a hidden DOM, right? For like SEO purposes.
For tab order.
Right.
Yeah. There's jank introduced by like bad architecture, or like I should say retrospectively bad architecture, because all of it is like historically contingent and was like more or less supposedly the appropriate idea at the time, or like there's a justification that you can make at the time that the decision is made.
It's crazy.
We'll add web canvas.
I heard this story. It was like a Y Combinator story of the company, the Y Combinator startup that eventually got bought by Google and became like Google Slides and Google Docs. But really, Google Slides is I can't remember who, but it was, they were talking about like how awesome these in like the web boom, the like project showcase within the YC batch was, how exciting it was. comparing it to AI today, and he's like, yeah, we went down and we saw these guys from, name of company, they were doing animations in the web browser. And I didn't know that was possible. And like the thing that was like, wow, this is groundbreaking technology, is like some guys have figured out how to like draw rectangles and have them move on the screen in the web browser to do a slide presentation.
In the web browser.
Yeah.
Our civilization has leveled up for having.
Yeah, they were like, whoa, dude, I didn't know you could do that. That's so cool.
Yeah. We can go to the moon and animate a web page of us going to the moon.
Yeah, how do you do this?
Yeah. Yeah, so there's that common pattern of just like you make the really complicated high level thing first, and then you try to invert it later. And so I would not be surprised at all if Quick currently or at some point never didn't have unreliability, even though it's again on application layer unreliable streams, unreliable datagram sends, and like only later added some extension for unreliability, or like doesn't have unreliability still, because it's the web. Then by the way, the QUIC stands for, I think it's like Quick UDP Internet Connections. I'm pretty sure.
Right. Which is exactly what they deliver on that very well.
Yes. It's certainly, I'll lay out how it's quicker than TCP in a second here. Or sorry, TCP TLS in a second here. So in this after this hello is sent, again, we have because we're doing this on UDP, we're gonna have the application take responsibility of whatever amount of orderedness or reliability that it wants to get into. By the way, I want to point out that technically ordered data and reliable data aren't strictly like mutually inclusive or whatever. You can have ordered data without being reliable, and you can have reliable data without being ordered. But it would just be like on a packet level or something. But
you also have to deal with duplication manually here, right? You can have, if the network on the internet accidentally duplicates your packet, it will arrive twice, and you have to deal with that.
Yeah, and well, if you just put a sequence number on the packet, well, then you just discard the second one. But you do have to remember that you got the first one. But yeah, there's ways to do that. With reliable unordered, it's really easy because it's just you resend and then there's just no number on it, or there's like a number identifier on it, but it's not ordered with respect to other packets. And then like the API on the server can just like receive that packet, and it's guaranteed to eventually receive that packet, but it's not necessarily before or after any other packet. Conceptually, that's kind of like if every packet was on its own channel, and then like you have no head of line blocking with respect to any packet because they're all unordered. But sorry, I guess that's kind of tangential. Point being, you're going to have the client send this hello, and the server is just going to respond again on UDP. I'm not specifying the ports here, but we can talk about that in a minute.
The ports are irrelevant. It's an extension of IP address, as far as we're concerned.
Yeah, sure. Yeah. And then the server sends, I'm pretty sure, it sends its hello and its cert.
They did a key political thing here with Quick, in that the Google guys making Quick in order to make sure that the web community would receive this well, perform no innovation on TLS, right? They actually still use TLS. They just use it better. But it's still the same TLS 1.3. You still have to link OpenSSL, because that was not the problem.
Right. So you're saying it's the same like encryption schemes. It's the same like cipher suites or whatever.
In fact, I'm pretty sure it's the
system
same
of certificates.
It's the same hellos.
Interesting.
I'm pretty sure it's the same
so
hellos,
it's
or like
almost
lightning
the same
modified.
Byte data, byte-wise.
Yeah, I think so.
Like very, very close. Okay.
Yeah, quick is basically like in the beginning here is like I'm not sure about this, but if I had to guess, it's the same TLS payloads that are like wrapped in these quick packets during this initial setup.
Right. Yeah. Yeah, I see what you're saying. Yeah. But notably, it's TLS 1.3, so we're not doing the thing where we send the like, oh, here's the encryption scheme upgrade, and then the client's like, oh, here's my encryption scheme upgrade. Okay, we're on the same page now. Oh, and here's my certificate, and then we get through. No, it's just like, you will use this one, or like you pack it in so that like, I put it in my hello, so it's like I can use this, I can use this, and I can use this, and I can use this, and it's just in there.
Yeah.
So
and
it's
TLS 1.3, so it's 2 round trips. So by using UDP so far, we skip 1 round trip, which is good.
Yeah. So Quick has I want to point out, this is the establishment of the connection, of the supposed so-called connection, and the TLS hello message in one packet, bundled in one packet. I don't know if it gets fragmented ever. I would assume not. I assume that's in the spec. I guess UDP packets don't. UDP goes over IP, so they can get fragmented, but
on IPv4
you can set the don't fragment bit.
They probably have some scheme for dealing with if the TLS data is too big to send it over multiple.
Yeah. And then at this point, we can just sort of like do the look back at how TLS worked, because it's basically just the same thing. Like the client sends over UDP again the what is it? The like I'm finished message, which is just like, yeah, I agree to this. I've authorized you. Here's my public key.
And the Diffie-Hellman stuff we're doing now.
Yeah, the public key and the Diffie-Hellman. And then I think actually there's also a Diffie-Hellman in here. Or again, it's kind of not so...
Well, no, because I don't know. It might be... I think that the Diffie-Hellman is encrypted using the client public key.
Right. Yeah, I could buy that.
Yeah, because I think they for security reasons, even though the Diffie-Hellman can happen out in the open, I'm pretty sure they want to not have them out in the open, just to be extra sure.
Yeah, exactly. And then of course, I don't know if there's a double Diffie-Hellman happening, but I just want to check real quick. I want to make sure I don't.
You want to make sure it's a factual podcast video.
I want to, yeah. I'm fact checking, real time fact checking. So yeah, the Diffie-Hellman happens in there, and this is part of the like finished message. So like I'm finished. I'm done. I'm ready to actually send you real data, and so again in this UDP packet, or maybe another UDP packet right after, but it's not subject to like a round trip delay. We have our actual HTTP GET request. And this is a multiplexing protocol, so it's much more complex, where it has the ability to specify like, oh, on stream channel number 1, I'm going to send you a GET request for this, for the web page. And this is going to come through, and then the server can respond with like on UDP with the actual data. And this is going to be like a HTTP response or whatever. And so the time delay from the client wants to establish a connection to we are sending real data, or the server is responding with real data, is like 2 round trips. It's like 4 packet deliveries. Whereas with TCP and TLS, it's like, again, we talked about it. It's like 1 round trip just for TCP, and then another round trip just for TLS, and then another round trip for TLS, And so that's like 3 round trips before we start sending the HTTP request. And that's not including the DNS request at the beginning. And with Quick, it's reduced down to like 2, or like it's kind of 1.5, because you can start sending the GET request like basically as soon as you've finished establishing the connection.
Right.
And so yeah, Quick is a big win relative to TLS and TCP. There's systems engineering happening here where you don't have any change to the DNS, so there's a round trip there still,
or it's in cache, but whatever.
Or it's in cache, but yeah, it might not be. You don't know. I mean, I'm pretty sure Quick has support for like re-establishing a connection that's long-lived.
Well,
so
no, they have
migration,
and they added some stuff which I think is probably a little bit too complicated for my taste. But they have this whole setup for if I'm on a mobile phone and I was on Wi-Fi and I turn the Wi-Fi off. Now I'm on mobile data. I want to maintain my connection across this boundary. So I need to be able to show up to the server from a different IP address, convince the server that, hey, this is that same session. I need you to change the IP address you associate with this with this session to be me. But they still have to they have to do that like in a way where they don't leak privacy details. So they do this thing where like at the beginning they establish many session handles that the client and server know about, so that when the client switches from off Wi-Fi to mobile data, it will use a different session handle so that it looks like a different session to everybody else, but then it arrives at the server and the server is like, aha, it's this guy.
It remaps it back.
Yeah,
that's really cool. I'm a fan generally of migration, just because I usually work on projects that where the user experience is a little bit hindered by migration. I think the more important thing is that I'm on IPv4 very much of the time, and so I'm dealing with users who are on IPv4.
You still have this problem on IPv6 if you switch network, like if you switch Wi-Fi network or something like that.
And so I like to have. I don't know how much of like my market share for like a game, for example, is actually subject to like gamers who are on a laptop in the coffee shop and then go home, like walk home,
and then they want to stay logged in.
A bigger deal for mobile. Yeah, they want to stay. They want to stay playing their rollback,
the MMO
fighting game session.
Yeah, the fighting game rollback.
They're like on the train. On the train.
I've seen that Steam Deck. There you go, Steam Deck.
Steam Deck. Yeah, that's why I think mobile drives a lot of these decisions.
Yeah.
Even though the web is still not designed very well for mobile.
I think that it's like complexity that seems a little bit overkill to me, especially when you get into the like privacy, have many handles, etc. The strategy I prefer is like, hey, we made it really quick to establish a connection, so we can just do that again, and then especially like the video game, for example, already has to have this concept of you can't be playing from 2 places, like you can't with your Steam account be in this game twice. So if you can connect again on the new network. Oh, and then also the games all support reconnecting to games. Like, Apex Legends did the very smart thing of my game crashed because the Apex Legends people did a goof. But if I can start my game again quickly, then as long as my friends made sure I didn't die, the game starts up, recognizes that, oh, I'm in this game, let me reconnect to that game and go in.
Yeah, that is one aspect. There is a bit of it puts more responsibility on the application developers to make sure that they don't be a bozo with reconnecting. But I'm generally in favor of stuffing more stuff into application layer and less
Yeah.
stuff into OS layer. It's just critical for
Being able to
reducing
ship a
like
good
bloat and
experience.
technical debt. Yeah, and shipping a good experience. Yeah, absolutely. I guess the last thing I'll say about Quick is that, again, because all of this is now UDP, it's all application layer. So Quick, quote unquote, reinvents or just redoes all the sort of congestion control algorithms. Again, the multiplexing I talked about, connection establishment and maintenance code that would have been in the operating system otherwise. But it means that Google can like deploy updates to those algorithms like just by updating Chrome, and it's much faster to change, and also um, it's it can be it's able to be inspected and understood by application developers, and like you can use Quick if you want, or use a variation of Quick for your game or your
Yeah.
whatever.
There's also a key
Without
advantage that, before I mentioned this discrimination you face as a UDP user, because UDP users are preferentially dropped. Well, now if we imagine that the entire world moves to UDP thanks to Google, even for the boring web traffic or the Netflix stream, then this discrimination will cease because there won't be a two-tier packet system at the base of the network stack. Everybody will be using the same type of packet, and so there won't be. Everybody will definitely be dropped equally, and so congestion
yes,
control will begin to work again for your video game and for the Netflix stream.
yeah, exactly. And the one thing that I was going to mention, the tidbit that I read about, was that you mentioned this thing about UDP packets getting preferentially dropped, but there's a related question of like, okay, middle boxes and just people in like in the office net router or whatever. Oh, there's all these firewalls. Do these firewalls block UDP packets? And if so, which ones do they block? And specifically, which ports do they block? And now on web connections, the usual port to send is on like port 80, like I said, or port 8080 or 443 or whatever. That's for TCP. TCP ports and UDP ports are usually handled differently. And it just so turned out that Google did this sort of like network test, way back whenever they made this protocol, maybe 2015, where they just started like sending out UDP packets on UDP port 80, because they wanted to see like, okay, what portion of like the internet actually like blocks port 80 on UDP, because nobody ever like thought about that because it wasn't relevant. Like there aren't any other applications that use UDP port 80. And they looked at it and it was like 70% of the traffic they were sending was just accepted and like sent through on port 80. So one of the key reasons that Quick was able to be created or was able to be deployed was because everybody just sort of forgot to block port 80 on UDP, and so everything was just going through.
Right,
so
right,
Google
right.
got to,
Yeah,
like,
it's the
deploy this
typical
update.
like network. I remember, like even say like the Luke Smith tutorial for setting up, becoming a internet lord and having your own internet land with a VPS web
Yep.
server. He's like, oh yeah, now we do the firewall thing. Remember, run this command to unblock port 80, UDP, and TCP. Right, and it's like, like that's just
Yeah.
the cargo cult. Everybody's like, oh, I gotta unblock port 80, TCP or UDP.
Yeah.
I don't know what the difference between those
Both.
are. So, I guess both. Yeah.
Yeah. So it was a really interesting like maneuver by Google to like be able to deploy this. Oh, and by the way, the ulterior motive that I want to mention, the cynical like political motive or whatever that you can accuse for Google for Quick, aside from the like nice fuzzy benefits, is that when you use Quick, if you're doing application layer encrypted connections across UDP port 80, it's because it's encrypted and it's not TCP. It's a lot harder for middle boxes and like the Office router to sniff those packets. It's a lot less clear what's actually going on there because it's just a UDP packet on port 80 from this IP to this IP. We don't really know anything more than that, other than like maybe this is the fault of Google Chrome. And if we were to get the entire internet to go across that, or like everybody on the internet to just be sending their web requests on port 80, well now like, you know, ISPs can't even really do like, you know, anti-net neutrality stuff where they try to kill all the Netflix, all the YouTube connections.
Well, actually, they can still do it, but the reason they can still do it is because they look at the IP address and say, "Hey, this is that IP address we gave to Netflix." Huh? Wow.
Yeah, exactly. Yeah.
Or even
so it's like
this is the specialty Netflix box that we installed for Netflix for both of our benefit, so that there's a Netflix server with a bunch of cached content close to everybody.
Yeah, exactly.
But it doesn't apply to
they have all the
to the small guys, or like basically not these, anyone who isn't these giant players becomes immune to net neutrality stuff, which honestly is probably kind of the best of both worlds. You get the gains of both having net neutrality and not having it.
Yeah, that's an interesting point. But yeah, it's like one more layer of defense that like Google can have for its like encrypted connections against like the Starbucks Wi-Fi and the well, maybe not the Starbucks Wi-Fi, but like just this general political wrangle, like tug of war between the browser people or the web people, I guess, and like all the like interested parties serving the web.
Yeah.
So I think that's excuse me. I think that's more or less all that I can think of to mention for Quick. Again, all this is application layer, so all the encryption has to be in application layer. All the like, there's not even an opportunity really for the OS to do encryption, which it could have in other cases. And there's it all has to be, all the packet delivery reliability is all application layer, but it also gives a lot more power to the application, which is a good thing in my opinion, at kind of a little cost, like a pretty small cost. And
it actually makes
the multiplexing system.
It makes for example, retconning in of unreliable transport to Quick wouldn't have to be a retcon. It could just be, well, we updated the protocol, and you know, if both sides support this new version of Quick, then we can just talk differently.
Yeah, exactly. And so the quickness of Quick comes, again, in this decrease in the initial latency on connection, which is actually ends up being pretty important on the web when you're like blasting a bunch of like separate connections for like all these different images, all these different, or maybe from like different servers. But it also gives us the ability to do multiplexing, which is, again, I mentioned this is really important. I want to stress this. If you have some sort of reliability layer, being able to spread out the data across many different channels that don't have to be ordered with respect to each other allows the effect of head-of-line blocking to be significantly mitigated. Because if you drop a packet on one channel, you can still process and deal with data that comes in on another channel at the same time without having to wait for the whole stream to be pulled in. I think this is one of the things that really kind of made me like angry and like not like the way that just people generally think about networking. I don't know how normal this is. Maybe I'm just repeating stuff web people already kind of know and just don't do that much about. But the multiplexing really gives Quick a leg up on the speed, because it means the effective latency is way reduced, because you don't have to wait for every packet to come through before like the end of your text or the image file comes in. And it really reduces the latency on the possible latency for a web render, for an equivalent web render.
It saves the like complexity soup that arrives after this stage in HTTP land, or even passing the HTML document, and now you have to fetch 2,000 different files. Those can be 2,000 different streams, and if they're all coming from the same server, which is often the case, well, then you can pretty much be maxing that connection and handle the packet drops very gracefully in comparison to the old system.
Yeah, I'm actually a big fan. It's kind of a meta point. I'm a big fan in networking. I mean, I could be disposed of this opinion later because I'm 25. But the idea that you have one connection that like subsumes as much of your application as possible, as much of your like experience as possible, is really attractive to me. This idea that the server, the Facebook.com like Facebook Messenger client experience is all getting blasted through one UDP connection. It is really attractive. Sorry, excuse me. Been sick lately. It's really attractive to me because it just, again, in terms of complexity, really self-contains everything in a way that's really nice. And again, it reduces the overhead of establishing new connections because you don't have to.
Yeah, it's also
I think that's all
it's more the system complexity on the other end, right? Because like in theory, like okay, more connections, whatever. The thing that's nice about that is that means there's actually one server that has the stuff on it instead of this like modern web thing where it's like our web application is a suite of machines. In fact, it's a suite of virtual machines that are like spun up on this whole cloud thing. For scale, we have this giant, multiplex at the front. They could take like 1 million connections and like give them out to a bunch of servers, and then you're suddenly in this like giant sprawling, load balancing, all these things. There's so much to do, and then it gets very hard to like run the server in the debugger.
Yeah. You can't run the distributed database that has load balancers and proxies and caches on a laptop.
Yeah, and the great thing about like, it's one UDP connection is like, it's one UDP connection. That like means it was one program communicating with one other program, which is trivially debuggable compared to any of this other stuff.
Yeah, absolutely. You want to minimize the number of, I would even say like parallel processing happening.
Well, you want to minimize the amount of nodes in your distributed system, right?
Yeah, exactly. Otherwise, you have to just resort to like a bunch of logging, and it just becomes really. And you have forensic
all the, like, chaotic team shows up to investigate the crime scene.
Exactly. Yeah, you have all the chaotic like chaos theory coming out of like that you had with the internet, but just happening again inside your distributed system. Or like, this partition failed in a way that didn't have backups, and now it's causing like a fallback, a domino effect that destroys your whole system unexpectedly. The 99 percentile latency target that you hit was getting like multiplied by the 99 percentile latency of the next microservice, and they all multiply to get like a 1 second latency because you didn't think about how the math adds up. It's just really like complex stuff that I hope to never deal with that much.
That's how you get the the Krazam video with the guy at Oracle, sitting behind the plant pod saying, we're very proud, we think the customers really notice how fast the token comes back. So we've we've really put in the work and managed to reduce increase latency by 30%. Where we hope the customers enjoy this continuous improvement.
Yeah, it's so demoralizing, at least for me. I don't know if I could. I might end. I don't want to put a death spell on myself where I like say I'd never want to work in that environment and end up working in that environment, because that happens. But I'm crossing my fingers. But anyway, yeah. So I think that's all I had to say about Quick and TCP, TLS, and HTTP. But I'm interested in if there's anything else you wanted to cover, and what's your deal? What's your problem with all this? Why can't we just keep going living this life?
Yeah. I mean, there's a little bit of encryption stuff, but I'm thinking, we've been doing this for 3 hours. I don't know how much time you have. It might be convenient to take like a little bit of a break and then come back.
Yeah, I'm down for that. Okay. Are we going to cycle the recording, or are we just going to do a break?
Yeah, I feel like we terminate all the recordings and then we'll set them up again afterwards.
All right, sounds good.
Okay, I'm going to terminate my phone.
All right.
End the stream, all these things.